for international collaboration and knowledge exchange in the field of sustainable metallurgy and hydrogen-based metallurgy. This symposium focused on the advancement of hydrogen-based metallurgy technologies and research, including hydrogen reduction, hydrogen plasma metallurgy, sustainable steelmaking, and alternative reducing gases for metal extractions and refining process. Throughout the day, participants will have opportunity to engage with distinguished speakers and researchers from Indonesia, India, and Australia through insightful presentation and discussion. Before we begin the symposium, let us take a moment to pray according to our respective belief so that today's event may proceed smoothly and bring meaningful impact for all participants. Thank you for your participation. Next, before we begin the symposium, we kindly ask all participants to pay attention to the following safety induction.
Safety induction, keamanan, kesehatan, keselamatan kerja dan lingkungan di ITB. ITB berkomitmen untuk mencapai kinerja terbaik di bidang keamanan, kesehatan, keselamatan kerja dan lingkungan yang mencakup aset sumber daya manusia, bangunan, peralatan, dan kekayaan intelektual. Oleh karena itu, ITB mengharapkan kesadaran setiap individu yang berada di area ITB untuk turut berperan dalam mewujudkan kondisi keamanan, kesehatan, keselamatan kerja dan lingkungan yang kondusif dengan memenuhi pedoman keamanan dan K3 yang berlaku di lingkungan kampus ITB sebagai berikut. Setiap individu diminta untuk meluangkan waktu memahami lokasi kegiatan dengan melihat peta lokasi yang memuat jalur evakuasi, lokasi pintu darurat, tempat berkumpul darurat, tanda kedaruratan, lokasi pemadam api ringan, dan kotak P3K. Terdapat pintu darurat dan assembly point atau tempat berkumpul yang aman di setiap gedung. Jika diperlukan evakuasi, panitia pendamping atau satpam akan memandu. Setiap individu wajib turut menjaga kebersihan gedung dan area dalam ITB, serta membuang sampah pada tempat sampah yang telah disediakan. Setiap individu diimbau untuk tidak meninggalkan barang tanpa pengawasan karena alasan keamanan. Tidak diperkenankan merokok di dalam gedung dan di kawasan kampus ITB, kecuali di area merokok. Harap dipahami bahwa keberlangsungan kegiatan dan acara adalah di luar dari pelatihan keadaan darurat. Jika alarm tanda bahaya terdengar, maka nyata terjadi kondisi darurat. Jika terjadi kondisi darurat atau menemui benda atau orang mencurigakan, kecelakaan, atau kondisi tidak aman lainnya, silakan menghubungi petugas keamanan terdekat atau nomor darurat ITB di 022 250 02 04 untuk area ITB Ganesha dan 022 860 10 020 untuk area ITB Jatinangor. Demikian pedoman ini kami sampaikan. Terima kasih atas kerjasama dan perhatian Anda. Utamakan keamanan, kesehatan, keselamatan kerja, dan lingkungan.
Ladies and gentlemen, we will now sing the national anthem of the Republic of Indonesia, Indonesia Raya. We kindly ask all audience to stand. Thank you. You may be seated. Next, we are honored to present a cultural performance by Mahagotra Ganesha. Mahagotra Ganesha is a student cultural organization dedicated to learning, preserving and promoting the rich heritage of Balinese art and culture. Through their performance, they bring not only the beauty of the traditional Balinese art, but also the values of harmony, spirituality, and cultural diversity that represent Indonesia's culture identity. So, without further ado, please enjoy the performance. Okay. Thank you, Mahagotra Ganesha, for such a wonderful performance. Please, once again, please a warm applause for Mahagotra Ganesha. Distinguished guests and participants, now we would like to invite Dr. Imam Santoso as the chairman of the symposium to the podium for his inaugural address. To the respected Dr. Imam, the stage is yours.
Assalamualaikum warahmatullahi wabarakatuh. His Excellency Bapak Aceh, Bapak Wakil Rektor, Vice Dean Bapak Taufik Hidayat, Bapak Zulri Zulhan. Actually, this is his mastermind and his colleagues from India. And I want to say thank you to Dr. Arup. Actually, he is not here. Unfortunately, he has some problem with his passport, but he will join from online, from Zoom. And also, I want to welcome the speakers, but his colleague is coming here. First, Dr. Ashok, and then Dr. Argia, and also Dr. Rajkumar. And also from ITS, Pak Fahreza, give applause to him. And I see here Dr. Winnie, Pak Setiawan, and maybe from Zoom, speaker from Australia, Pak Baram Damni, and his colleagues, and all the participants who has come to this place. Okay. So actually, this symposium is, in this era of green energy, sustainability, this topic is really, really, really fun. So today, we listen to very, very prominent speakers. And the objective, of course, this one, we can exchange our knowledge. And what the most important is the recent update about hydrogen metallurgy from India, Indonesia, and Australia. As you know, in ITB, Pak Zul has create plasma hydrogen. Maybe it's become very interesting topic for India and Australia people to know what technique metallurgy done recently in the hydrogen metallurgy. And also we really want to know what India done and also Australia done. And this is really, really very important information for all people in Indonesia and India and also Australia. So this is the topic. The main theme is advancing hydrogen-based metallurgy technology for sustainable future. And this is the more detailed theme. So the main event is today, and tomorrow we will go to a game laboratory, which is very new for Indonesia, and it's really advanced. It is hydrometallurgy lab mainly, but we have some furnace, and I hope in the future this lab also will ready. Also, there is high temperature experiment also. So tomorrow we will bring you all speaker to another part of ITB, to the second campus. Actually, we have 3 campus. Here, the main campus, Jatinangor, and also Cirebon. This is the speaker. Firstly, give applause to Pak Zul, the man behind this symposium. And then Dr. Ashok, Bima Satriama, Fahreza, Dr. Fahreza, and also Dr. Raj Kumar. Indonesia is really close with India because you know, we have the biggest temple, one of the biggest temple in the world. We have Prambanan, and also we love Indian, Kuch Kuch Hota Hai. And we have from Australia, we have Miss Dian, and then Dr. Taufik Hidayat. Give applause to him. Dr. Arup. This is for the plenary session, and then actually this is also our previous student, Made Girinata and Sani Sofia, and also here Dr. Argia. Give applause to him. Sorry. Actually, we have 126 registered, but half is here. But don't worry, they are on their way, okay? They are on their way. I think it is around 70 people in this room, but it is quite okay. Okay, collaboration between 3 countries. And this is industry who already registered, and also university. We have PT Antam IC, Pak Pras already here. Also PT Borneo, PT Arsari, and also Kalimantan Nusantara Pratama. And this is it's involved 3 university from India, 1 university from Australia, and 4 university from Indonesia. Yes, and that's all for me. Thank you and welcome. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Imam, for the inspiring remarks. Next, we are honored to invite the Vice Rector for Finance, Planning and Development of ITB to deliver the welcome address and officially open the symposium. To the respected Professor Agus Jatnika Effendi, the stage is yours.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, good morning everyone. Bapak dan Ibu, since we have distinguished speakers from abroad here, so allow me to read the welcoming speech from our rector in English version. Anyway, it is already prepared by the organizing committee, so thank you very much. Distinguished guests of the Indonesia, India, Australia Symposium. First of all, let us express our gratitude to God Almighty for His blessings, allowing us to gather here today in good health and spirit. The metallurgical sector plays a strategic role in supporting industrial growth, manufacturing, and the global energy transition. The Global Critical Mineral Outlook 2025 reported a significant increase in the demand of lithium, nickel, cobalt, graphite, and rare earth elements, driven by the rapid development of electric vehicles, energy storage systems, and renewable energy technologies. However, many metal production processes still rely on heavily on carbon-based reductants such as coal and coke, which generate large amounts of CO2 emissions. The iron and steel industry alone contributes approximately 7 to 9% of global fossil fuel-related CO2 emissions. Therefore, cleaner and more sustainable technologies are urgently needed to support the decarbonization of the metallurgical industry. In response to these challenges, the use of hydrogen as a reducing agent has emerged as one of the most promising solutions, as it produces water vapor, H2O, instead of CO2 as a byproduct. This approach, of course, will open new opportunities for the development of green metals and supports the achievement of the net zero emission targets by 2050. It is a great honor for Institute Technology Bandung to host the Indonesia-India Australia Symposium on Frontiers in Hydrogen Metallurgy, organized by the Department of Metallurgical Engineering ITB on 21st, 22nd May 2026. The symposium serves as an international platform that brings together expert researchers, academics to advance hydrogen-based metallurgical technologies. Through this symposium, we hope to strengthen the innovation ecosystem, support the global energy transition, and accelerate the development of alternative reductants to replace coal and coke. Key discussion will focus on hydrogen-based reduction, hydrogen plasma metallurgy, critical metal extraction, and the roadmap towards a greener industry. In closing, on behalf of ITB, on behalf of the rector of ITB, because he is away now, he is in China, for any other collaboration to make it ITB much, our target is the 150 world-class university, so our rector has to visit many universities to make a collaboration. So he cannot attend this symposium. So on behalf of him, I would like to express my sincere appreciation to all speakers, especially from India, all the way to come to Bandung. Thank you very much. Distinguished guests and participants for joining us today. May the symposium become the beginning of impactful international research collaboration that will shape the future of the global metallurgical industry. So, with gratitude and great enthusiasm, I, once again, on behalf of Rector ITB, hereby officially declare the Indonesia-India Australia Symposium on Frontiers in Hydrogen Metallurgy officially open. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Professor Agus Jatnika Effendi, for officially open this symposium. Next, we will proceed to the photo-taking session. We kindly request everyone to simply remain in your seat and look towards the camera at the front. May the assigned committee members please take the position. For the participant, may you fill the empty seat first in the front, please.
Okay, for the participant, you can move forward. Okay, pay attention to the camera. I'll take the picture in 3, 2, and take a picture. Okay, once again, I'll take a picture in 3, 2, and take a picture. Okay, thank you for the attention.
Okay, thank you. Please give a warm applause for us. Next, ladies and gentlemen, we would like to welcome to plenary session 1. To lead this session, we would like to invite our moderator, Mr. Taufik Hidayat, PhD, to come to the stage. To Mr. Taufik, the session is now yours.
Okay, good morning everyone. Thank you for coming to this first plenary session. So in this plenary session we have a very interesting topics including hydrogen plasma smelting, ammonia versus hydrogen reduction, silicon production and purification, and also ammonia-based reduction for ferronickel production. So I would like to invite the first speaker, Professor Zulfiadi Zulhan, to come to the podium. Yeah, let's give a big applause for Professor Zulfiadi Zulhan. So let me introduce Prof. Zulfiadi Zulhan. Professor Zulfiadi Zulhan is a professor in the Metallurgical Engineering Department at Institut Teknologi Bandung. He earned a bachelor's degree in Metallurgical Engineering from ITB in 1996 and a master's degree from the same institution in 2000. He continued his study in Germany, earning his Dr. Ing from Institute for Ferrous Metallurgy from RWTH Aachen University in 2006. And from 2006 to 2009, he worked as metallurgist at one of the steel plant builders in Germany, where he was involved in commissioning carbon steel and stainless steel plants across China and the UAE. His expertise include advanced vacuum degassing technologies and also vacuum oxygen decarburization for stainless steel production. Now he is the director of the community service and expertise in ITB, and also his current research focus on developing fast and environmentally friendly metal production method, particularly through hydrogen plasma smelting reduction. And Professor Zulfiadi Zulhan, you have 20 minutes for presentation, and there will be someone showing you if you have remaining 5 minutes, and after that we will continue with Q&A. So Professor Zulfiadi Zulhan, the podium is yours. Yeah.
Thank you, Dr. Taufik Hidayat, for the introduction. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Good morning, everyone. First of all, I would like to warmly welcome our distinguished speakers from India, Dr. Arghya Majumdar, Dr. Arup Kumar Mandal, who is joining us online, Professor Raj Kumar Diswar, Professor Ashok Kamaraj. We are also honored to have Professor Akbar Ramdhani and his team from Australia joining us online and sharing their expertise with us today. A warm welcome to all speakers and participants. We greatly appreciate your presence and contribution to this seminar. So now I will start my presentation. The title is Critical and Rare Metals Production from Their Oxides by Hydrogen Plasma Smelting. The Indonesian government has identified several metals as critical and strategic. Yeah, you can see from the picture with the red border line is actually the critical, and with the black color of the alphabet means the critical and also strategic. Today, I'll present recent research results from the Paro Metallurgy Laboratory on the use of hydrogen plasma smelting reduction to produce different metals, including iron, nickel, chromium, tin, molybdenum, manganese, titanium, silicon, zirconium, lanthanum, and neodymium. This slide shows the CO2 emission from producing different metals. The data include both scope 1 and scope 2 of the CO2 emissions. Nickel production has one of the highest CO2 emission because it uses a large amount of energy and also reducing agent. The metal industry produces about around 10% of CO2 emissions globally. So cleaner production technologies are needed to replace the current technologies. And the figures on the right shows the total CO2 emission from major metal industries. Still produce the most CO2 overall because much more steel is produced than any other metals. We know that currently around 1.8 billion of steel is produced worldwide, so a lot of CO2 emission coming from these industries. If we look to the Indonesian cases, actually Indonesia, we produce a lot of emission coming from the nickel industries. This is the breakdown of the CO2 emission from each step for the iron and steel production. The biggest one coming from the blast furnace, 1.5 tons of CO2 per ton of steel produced. Also, during the preparation of this material, before we charge to the blast furnace, so CO2 also emitted from the coke plant and also from the sintering plant. And the other one, also some of CO2 emission is also produced during the hot rolling mill because we need to heat up the slab or the billet before we form it. And actually, if you talk about the reaction, it's very easy. The key also here to produce metal, how we remove the oxygen, in this case is from iron oxide. If we use carbon, so CO will be emitted. It depends on the source of carbon. If we use a fossil source of carbon, for example, coal or coke, so the CO2 emission cannot be recycled back or the CO2 emission stay there on the surface. In other case, if you want to make the process more neutral, so you can use biomass. In that case, we need huge area for plantation, and also it takes a longer time until we crop the plant and process it to the charcoals. And up to now, and actually start from this day, more people, a couple of years ago actually, most people try to use the other alternative. That's not new actually. Hydrogen has been make a lot of research in the last 30 years, but now we really focus whether we can replace the carbon sources as reducing agent by hydrogen. In that case, we produce water, and this is the current technology what we use today to produce iron and steel. If you look from this technology, so there's some effort to replace some coke with biomass in the blast furnace, and also there's a lot of trial and pilot plant has been constructed, including also the initiating of the plant construction by using this technology, shaft furnace and free dust bed reactor, by use hydrogen as a reducing agent. In that case, we can minimize or we can reduce the CO2 emission from iron and steel making. And the other alternative, we can also use electrolysis, high temperature or low temperature. The molten oxide electrolysis is already established in pilot scale, including also Volteron for the low temperature of the iron making. And the new one, this is not new actually, the other alternative is by using hydrogen plasma smelting reduction. If we talk about the charcoal in the blast furnace, it's not new actually. Before the Industrial Revolution, we have used the charcoal as the reducing agent. Before 1850, roughly, we have used this kind of reducing agent. This kind of plant still in operation in Brazil. This is one example. In Brazil, they have the blast furnace with the volume less than, in general, it's less than 1,000 cubic meters. It's better to have the blast furnace, small blast furnace, less than 500 cubic meter. So in that case, we use the charcoal as reducing agent. The consumption is around 450 to 700. But the problem is we need huge area for plantation, that kind of plantation. So we need a huge area to produce wood in order to supply blast furnace for the iron making. And this ongoing construction plan in the world. The first one is actually the hybrid, now it's under construction. I think at the end of this year or at the beginning of next year will be in operation. They replace the blast furnace with the shaft furnace, hydrogen shaft furnace, and the derived from the shaft furnace will be processed further in AIF. And the other one, the idea is to replace the blast furnace by using hydrogen shaft furnace and combine with electric smelting furnace. And this plant is now under construction in Germany, in Duisburg, by ThyssenKrupp. And they want to keep actually the existing basic oxygen plant in order to produce high quality steel. The other one is Hyrex. It's now under development. It takes time. Maybe at 2030, it will be in a pilot plant. If we talk about the green steel, it's actually expensive, very, very expensive. The first, we must think about the hydrogen requirement. That one is to produce 1 million ton of steel. We need roughly 75 kiloton of hydrogen, and this is the power or the energy requirement, and this is the power requirement for the electrolyzer in order to produce 1 million ton of steel. Can we imagine if you want to produce 1.8 billion ton of steel, how many gigawatts of the power generation is required for the production of hydrogen? It's really expensive actually. Because of that, the people for sure that the blast furnace steel, if we would like to produce steel in this day, so we will choose blast furnace because that one is the efficient one and they can produce the steel with high capacity. This is the publication from Japan in 2025 from Professor Ariyama. He showed that blast furnace still in operation until 2050, and there is a lot of modification was conducted or is proposed for the blast furnace in order to reduce the CO2 emission. And start from today, actually, the shaft furnace, which use hydrogen and also free gas bed with hydrogen as reducing agent, will be installed in the industrial scale in order to reduce the CO2 emission. And the other one is actually, we can also use scrap. The problem is the scrap is scarce. It's not easy to find the scrap. The scrap is not available. And this one example in order to improve the process in the blast furnace. And this plant, according to the latest news, in April 2026, last month, and one of this plant will be installed in India at Tata Steel. And in this case, the CO2 emission can be reduced from around 1.8, 1.7 to less than 800 kilogram per ton of steel. In that case also, we can reduce the coke consumption to 100 to 150 kilogram per ton of hot metal. This is one way, yeah? By using carbon is one way. The current processing is we use carbon and acetic acid and we use blast furnace. And the other one is we use hydrogen in the form of diatomic to produce iron. In that case, we use shaft furnace or free gas bed reactor. And this is actually the other alternative way in order to produce metal. We can also convert the diatomic hydrogen into monoatomic and also into ionic. Maybe some of you understand this diagram. If we look from this diagram, it means that if we move the line from the top here for hydrogen to this line to use monoatomic hydrogen, and also to this line to use the ionic hydrogen, it means all oxides can be converted into metal, all oxide. If you have the soil in front of your house, you can take it, bring it to laboratory, and you can convert the soil into the metals, mixed metal. This is theory. It's theory like this, but it's not possible actually in the reality. And this again, if we talk about the hydrogen plasma, so the temperature should be more than 16,000 or more than 10,000 degrees. At that temperature, everything evaporates. We have nothing inside, everything in the gas phase. It's a big challenge actually. If you look from the iron diagram, so after around 3,000 degrees, so in that case, everything is in gas phase. So maybe it is not possible directly to produce metal at higher temperature because everything is converted to the gas phase. If you talk about the hydrogen plasma smelting reduction, actually it is not new. A lot of research was conducted in the last 40 years or 50 years in order to produce metals, and a lot of institutions in the world working in this area. Now I put also here IIT Dhanbad. You work also in this area. And this Dr. Arup worked in also with the hydrogen plasma. also with Swinburne University, and we have a lot of connection with them. And we have developed it in 2023, the hydrogen plasma lab scale hydrogen plasma smelting reduction. And the first time we have made a trial to produce iron from limonite iron ore, the content of iron roughly 58%. In that case, in 1 minute, you can see from that results, this result, we can also produce iron already, metallic iron, but it's not completely reduced. There are still iron oxide in the slag. If we increase the time to 2 minutes, in that case, we can convert directly this ore into the iron, or we can call it more like steel because there's no carbon inside. Just put alloying element and then we have steel directly. And we have repeated the experiment more than one time. We have similar results. And we have published some articles in the last 2 years, 1 to 2 years, regarding to the iron production and also recycling of nickel leaching residue to extract the iron, how to produce ferronickel, ferrochromium, and direct production of stainless steel. In lab scale, all is possible. This is one of the results. In this case, we have the raw material from the nickel leaching residue. In this case, the sulfur content is 1.55%. And we can reduce the sulfur content from around more than 1% to less than 0.1% in roughly 3 minutes. This result also confirmed the experiment results by the other researchers, by Sosa Filho in 2021 from Germany. Also the same, we can also remove sulfur, phosphor, and also remove the other impurities. Also similar, which was reported by Dr. Arup Kumar Mandal and team. He has also made publication how to remove carbon, silicon, and the other impurities in the molten pig iron or hot metal by using hydrogen plasma smelting reduction. And we have also conducted the experiment for ilmenite concentrate. You can see the results here. So we can reduce the iron oxide in the slag less than 1%. And this is the titanium content in the slag. It's more than or close to more than 90%. We can achieve it. But we can achieve it only in lab scale. I think in the production scale it's not so easy, it's very, very difficult because the viscosity will be increased by reducing the iron oxide content in the slag. And similar result also has been achieved by using iron sand concentrate as raw materials. In this case, we can also increase the titanium content more than 70%, and the iron oxide content less than 0.5% is typical of the slag composition and typical of the metal composition. Interestingly, we cannot reduce the titanium. That's actually our aim. Whether we can also have the titanium inside the metal, but it's not possible actually. We have increased the time until 10 minutes, and the initial aim is actually to produce directly ferrotitanium by using ilmenite or iron sand concentrate, but it is actually not possible. And we have also made an experiment by using red mud as raw materials. This is the result. You can reduce the iron oxide content in the red mud in 2 minutes, or we increase the time so we can reduce again less than 1% the iron oxide content. And by doing that, we can also increase the content of the other maybe critical metals in the slag. And then we can process it by using hydrometallurgy. This is the result around 3 months ago, in 2026, whether we can also recover the iron from the copper slag. Yes, it's not so difficult, it's very easy. It's actually by using hydrogen plasma smelting reduction. You can see here the iron oxide content. And we can also reduce SiO2. And by using the copper slag, so there is sulfur. We can decrease the sulfur content to less than 0.1%. And the other thing, it is very difficult to remove the copper. It's not so easy. It takes time. Maybe if we extend the time to 15 minutes, so we can reduce also the copper content. If we put this kind of reactor in this complex process route, so we put the hydrogen plasma smelting in this area, so it means when it works, we can replace the blast furnace, we can replace the other thing, iron making and steel making, we can combine it into one equipment. So this equipment actually can be used for smelting, reduction, as well as for refining. Yeah, we can remove sulfur, we can remove phosphor, we can remove everything inside. So the products actually still about the hydrogen content, we can remove it maybe if they're available, so we can remove it as well during the vacuum degassing technique. And this result from ferronickel production, we can produce it in lab scale. And this is when we talk about the ferrochromium. This is the current process to produce ferrochromium. We have a high carbon ferrochromium. If you want to produce low carbon ferrochromium, we need a double electric furnace for sure that the production cost will increase. It's the result from laboratory that we can reduce the chromium oxide, but maybe we don't know sure 100%. Maybe some of the chromium will be evaporate. Maybe some of them will evaporate. This is the estimation of the yield of the chromium. In that case, interestingly, that we can reduce the silicon oxide. Yeah? Silicon oxide can be reduced to SiO gas, and we can remove it. And we can see from here also the alumina content increase. It means that it is very difficult to reduce alumina into aluminum. If we can reduce it, aluminum will evaporate as well because the melting point of aluminum is very low, 660 Celsius degree. Here's the current process to produce stainless steel. The idea is whether we can produce it directly. We have mixed the chromite ore with nickel ore and put it in the reactor. At the end, at a certain proportion of chromite ore and nickel ore, we can produce directly the 300 series of stainless steel, principally. So one aggregate, this is the current process route to produce stainless steel, very, very long production route. We think that in future, when it is possible, so only one equipment is required, so it needs a preparation for nickel ore because there is crystal water inside to prevent the explosion in the HPSR. And then the product from here is actually directly stainless steel. We mix it together and we have directly stainless steel. It's like a dream in the future, not now. I don't know, maybe in 100 years later. And this is for copper and tin removal from steel because we use automotive scrap as raw material, so there's always tin and copper inside of this scrap. This is a big problem, big challenge today. And in this case, principally, you can also reduce the copper during the hydrogen plasma smelting reduction. The amount of iron evaporation is around 5 to 7%. There's some of the iron also will evaporate, and we have cooperation with Professor Yuichi Ushida from Nippon Institute of Technology in Japan, and the sample is actually coming from Japan. And this is if you compare the results of our laboratory compared to the other laboratory in the world. So the main difference is actually the amount or the concentration of hydrogen in the reducing agent. So we have 80%, in this case it's 50%, this is 10%, in this case around 2%. We have high amount of hydrogen. So now we go further to observe whether the other metal also can be reduced, can be produced also in hydrogen plasma smelting reduction. We look one by one. Okay, can I extend around 5 minutes? Yeah, okay. And in this case, we would like to know whether tin also can be produced during by hydrogen plasma smelting reduction. Theoretically, it's possible, but in reality, it's difficult, not so easy. We have tried, and this is the result. So this is the chemical composition of the tin metals, and we have seen here that the SNO in the slag is very, very high. So not all SNO can be converted. We don't know why. What's the reason? We don't know why. We have tested a lot of samples, a lot of experiments, but we have always similar results. Also for molybdenum, molybdenum actually from molybdenum oxide, we use hydrogen at temperature roughly 860 degrees to produce a molybdenum metal. And if we use hydrogen plasma smelting reduction, we can produce it, but also not so effective compared to the current process. I think for this case, to produce tin or molybdenum, we should select the current process. And for pyromanganese, also very, very difficult to reduce mangan oxide. Only small particle of metals is formed like that. And there's a lot of, the concentration of MnO is like still very high. So a lot of MnO cannot be reduced directly. And then we are thinking whether we can combine carbon and hydrogen plasma together. And this result, yes, we can increase the content of the manganese until 80% compared to the previously is less than 20%. And if you look from this diagram, also small amount of metal is produced, the other is actually a slag, and a lot of manganese in the slag. And similar also silicon, if we take SiO2 as raw material and we put it in the reactor, so it can also produce silicon directly because SiO is what's called intermediate product in the gas phase. So we have the losses of the silicon in the gas phase. And then if we put it together with carbon, actually similar to the current process, we use electric arc furnace to produce silicon. So it's difficult now, so easy to produce silicon. And also ferrosilicon is also similar, like silicon, we should also combine with graphite or biocarbon, similar like the actual process, the current process, to use electric arc furnace for the processing of the silica into the ferrosilicon or into the silicon metal. And then for ilmenite, we have tested until 15 minutes, 20 minutes, we cannot produce ferrotitanium. We need aluminum. But if we combine aluminum thermic and hydrogen plasma, we can reduce the consumption of aluminum for production of ferrotitanium. And then we go further for titanium, also not so easy to produce it. It's the content of titanium. Now the publication is under preparation. And the young guy, the other guy will join to make research in this area. We combine carbon, graphite, and hydrogen plasma in order to produce the titanium metals. For sure that the product is not titanium metal, but titanium carbide is the product because we use a carbon as a reducing agent. Aluminum, not possible. We have tested. A lot of experiment was conducted by using alumina as raw material and put it into hydrogen plasma. It is not possible to produce aluminum. And in this case, we use a bauxite as raw material to observe whether we can increase the alumina content in the bauxite. So in this case, if you do the experiment 0.5 minutes, so the alumina content is 25%. If we increase the time to 4 minutes, so the alumina content 73%. We can maybe refine the bauxite, maybe, I don't know. But in this case, we can only remove iron into the iron metals and SiO2 into the SiO gas. These two components is not easy. It's very difficult to separate it. Not easy. And then we go further to the zirconium. We have also, now is submitted to the Journal of Material Research Technology. We're waiting for the result, the final results. And we have also combined with carbon. And carbide is forming inside. But according to the research from Dr. Mandal, it means that we can also remove carbon during the hydrogen plasma smelting reduction. I don't know, maybe by extending the time, we can refine it. We can remove the carbon also, maybe. And this is the current process how to produce the rare earth oxide from the monazite. This is a long road to obtain each of individual oxide, cerium oxide, lanthanum oxide, etc., etc. And we have also made the experiment that phosphor can be removed also via hydrogen plasma smelting in less than 10 minutes, so we can remove it. And this is the experiment how to produce rare earth metals. Yeah, there are 3 students who are working in this area. Sunny will make presentation today about how to produce cerium, and the other one is neodymium and also lanthanum. This is the result from lanthanum. It's the raw material before smelting. After 1 minute, so we have that kind of metals, and we put it or bring to the laboratory to analyze it. This is the chemical composition. So still a lot of oxygen inside on the surface of this element. Similar, when we increase the time to 3 minutes, the content of lanthanum can be achieved in certain area is 97%, but there's still oxygen inside. And this is for neodymium. This is the result. So this is the raw materials and the products of metals. We can see from here is product of metals. Yeah, can be seen clearly. This metal is actually. And if we let the metal contact with atmosphere for a couple of days, so this is the products. So it means the metal reoxidized into neodymium oxide. So we have no experience. And then we learn that the product should not be contacted with water, should not be prepared like this. And then we make the other way to make analysis. So this is the result. This is the initial raw materials. This is the products, the metals. And we analyze the neodymium content, 93%, 91%, based on the experiment which was conducted 2 days ago. Where is Diaz? Diaz. He has conducted this experiment 2 days ago, and the result was sent to me last night. He has analyzed in a game laboratory yesterday. This is we're talking about the industrial scale. So now there's a lot of experiment is conducted to make it in the pilot plant, pilot phase, in order to produce the metal directly from oxide by using hydrogen plasma. Actually, if we look about the technology, we talk about technology, it's not new actually. This technology is already existing, this technology. It's used to produce ilmenite. So you see from here, they use nitrogen gas to inject the ilmenite inside the furnace. Actually, by substitute nitrogen or the other gas by hydrogen, the furnace is there. It's already available. Then we should take care about the safety, refractory control system, and then actually we can do it directly in the industrial scale. Now I come to the summary. Yeah, okay. Summary: the production of nickel, iron, tin, molybdenum, chromium, manganese, etc. has been tested using hydrogen plasma smelting reduction. The results show that nickel and iron are very easy to produce in hydrogen plasma smelting reduction. Molybdenum and tin are not easy to produce, and chromium is possible but relatively difficult. Manganese and silicon require additional reducing agent. Aluminum is very difficult. I say it's not easy, not possible to produce in hydrogen plasma smelting reduction. Titanium and zirconium are still challenging to produce. The result demonstrate the possibility of producing rare earth metals from their oxides, such as neodymium, lanthanum, and also cerium. The process may be not economical for large-scale steel production, because the price of energy, the price of hydrogen, but it could be highly attractive for small-scale rare metal production. Thank you very much for your attention.
Okay, thank you very much, Prof. Zulfiadi. So we have probably one very brief question. If you have any question, please raise your hand. Yeah, okay, Professor Raj.
Thank you, Professor Zulfiadi, for a nice presentation. I have just a small question. Did you measure the maximum temperature throughout the furnace?
No, we don't measure the temperature.
Okay. Okay. Yeah.
Okay, thank you very much. Yeah. So let's give another big applause for Professor Zulfiadi Zulhan for the very interesting presentation. So we should proceed to the second speaker. I would like to invite Dr. Ashok Kamaraj from Indian Institute of Technology, Hyderabad. So while we're waiting for the preparation, let me introduce Dr. Ashok Kamaraj. So his current position is Assistant Professor at Department of Material Science and Metallurgical Engineering, IIT Hyderabad. And his education, he did Metallurgical Engineering Bachelor degree in the Government College of Engineering in India, and then continued with his Master and PhD in the Council of Scientific and Industrial Research, National Metallurgical Laboratory in India. And his previous position, including Deputy Manager in Tube Product of India, Scientist in the Bureau of Indian Standards, Trainee Scientist in CSIR and ML, Senior Scientist, and now, of course, Assistant Professor at IIT Hyderabad. So he will give a very interesting presentation with title Gaseous Reduction of Iron Ore Ammonia versus Cracked Ammonia versus Hydrogen. So you, Dr. Ashok, you have 20 minutes for presentation, and then after that we have 5 minutes for Q&A. So the time is yours. Yeah.
Yes. Thank you for the brief introduction. So I thought I should tell you from where I am. Our institute locates at, just below the center part of India. The point I marked is the Hyderabad.
So I am from Indian Institute of Technology, Hyderabad, which is one of the premier institutes in India. There are several IITs. We comes under second generation IIT. The first generation IITs were started long back, and our institute was started from 2008 onwards. So they are the couple of buildings, beautiful buildings. Since it is a new IIT, if you come there, you will get to see the new buildings. And this is our iconic hostels, student hostels. There are a lot of thought processes involved in designing these buildings. So that's the lab, Sustainable Metallurgy and Industrial Technologies. That's the lab headed by me. We are 13 PhD students in my lab, and then a couple of other students like BTech, postdoc fellows, MTech. The key scientific issues we are addressing in our lab is, the first and foremost is the hydrogen metallurgy, then development of direct alloying practice, also certain aspects on extraction and refining of critical metals, which is very important nowadays because of the energy security and material security on national perspective. So broadly classified into, my expertise goes into green steel making, clean steel production, process modeling, molten metal treatment, metal recycling, slag valorization, and with the help of collaborators, I do apply artificial intelligence, machine learning in extraction processes. So these are all the running projects. Today morning, I told to some people I have a lot of PhD positions open. If some of you are interested, we can explore how that can be. They are the laboratory facilities. We have, starting from raw material raw material preparation to high temperature experimentations. We also into process modeling. You can see the electric arc furnace model. This is a BOF model, and that's a ladle model. And the 10 kg facilities for vertical DRI production, retard and the rotary kiln biomass or biochar based, and air induction melting, electroslag remelting. These facilities are under installation. So with a brief introduction about my lab, I'm getting into the topic. It's a gaseous reduction of iron ore pellets. So we want to understand the kinetics of iron oxide reduction when we use ammonia as a reductant, cracked ammonia as a reductant, and hydrogen as a reductant. Because there is a lot of things that is going around. Ammonia is a better, but we want to see which is better and what conditions. Before proceeding itself, I would like to thank all my students who contributed, because I didn't do even a single experiment. It's all by my students. So background, I think enough background is given by Professor in the previous talk. We all know that hydrogen-based steel making is going to be the future because of the carbon dioxide consumption that goes to be reduced. Various routes are there: molten oxide electrolysis, process integration, direct reduction, and hydrogen metallurgy. Out of this, what we are now going to focus is the hydrogen metallurgy. Hydrogen metallurgy, you can only call the steel making hydrogen when the electricity is green, because if the electricity is not green, then the hydrogen that you are going to use is not green. At least in India, we are still rely on 70% of electricity comes from coal-based power plants. So that means you emit CO2 not in the steel plant, but somewhere name called as a power plant. You'll be emitting. The another hurdle with the hydrogen is it is too light, and liquefaction is at extreme atmospheres, like high pressure and the low temperature is required, which is another hurdle for making hydrogen and then transporting hydrogen. Storage and transportation is still a problem. There are no materials which is defined particularly how, where, and the hydrogen can be stored for a long term and also transported. These all become a problem. So as I told, these are the numbers. You can see 350 to 700 bar is required to basically to liquefy the hydrogen, and it requires minus 253 degrees Celsius, which altogether put 7.1 US$ per kilogram, which includes some transportation cost also, right? So much of cost is involved in storage and transportation of hydrogen. So that's the reason the one important thing is ammonia come into picture, where almost 17% by mass of hydrogen can be stored in ammonia. And we all know that ammonia is the second largest used chemicals in this world. That means the transcontinental, logistics are established for ammonia. There are no problem with the materials for construction, materials for transport, storage, all these things when compared to hydrogen. Ammonia become a very easy choice. One can take ammonia for a source of hydrogen. You can see ammonia can be liquefied at 8 bar, relatively very lesser pressure compared to hydrogen, and also, at room temperature you can operate, not like minus 253 degrees Celsius. So the cost involved is $5.5 per kilogram of ammonia. So basically what happened, today iron and steel production is completely based on carbon dioxide, carbon-based process where it emits a lot of carbon dioxide. So the emitted carbon dioxide can be converted to methanol, ethanol, or some other chemicals. So that's, you need standalone industry of iron and steel production. Nowadays, not going to be a standalone industry. It has to rely on some chemical industry to convert this, waste CO2 to some production. At the same time, it also has to depend on the upstream, some other chemical industry, which is ammonia. So far it is a gigantic industry, but because of the decarbonization pressure, iron and steel industry is never going to be a standalone industry. It is going to rely on some chemical industries to make a net zero that what whole world is expecting. So the integration of chemical and steel industry is what the way forward. We know iron oxide Fe2O3, which is a hematite that goes several stages of reduction, Fe2O3 to Fe3O4, Fe3O4 to FeO and Fe, which is also followed for gaseous reduction. There is no problem. As we told, there are certain pros and cons with the hydrogen and ammonia, right? So the process-wise, the problem, if you see, when hydrogen is there, the melting behavior of the pellet need to be understood properly. And when ammonia is used, there is a nitrogen pickup is there during the DRI production. So the nitrogen is one, sometimes it is good for steel, sometimes it is bad for steel. Wherever it is used as an alloying element, there is no problem, but wherever it is seen as a detrimental element, you have to avoid the nitrogen. So ammonia comes from the nitrogen comes from ammonia. So there is a competition when you bring the ammonia into picture. There is a metallization versus nitridation. Metallization is what we want, nitridation we don't want. Okay? So that is the thing that we have to take. But the advantage of ammonia is in situ nitriding process protects the metallic iron. The present day hydrogen DRI, direct reduced iron, whatever we produce, that is prone for reoxidation, which cannot be easily transportable. There is a lot of problem involved in it. So the nitride forms at the surface of the pellet, which protects the DRI. Of course, I told there is an established transcontinental logistics and a low liquefaction cost for ammonia, which all actually puts ammonia as one of the options that need to be explored, if at all the steel industry is moving towards hydrogen-based reduction. So the options are, you can go with ammonia injection into the DRI vertical unit, or we can also explore ammonia injections into the rotary clean process, because in India there is close to 390 rotary clean units are operated. Rotary clean process is one another process where DRI is produced severely based on coal as a reductant. So there are options that you can introduce ammonia with biomass or without biomass. These all questions need to be answered. That's where we are started our working. With all this background, we went into experiment the ammonia reduction. That's the pellet preparation steps involved. Basically, we were worked on the dried pellets, and then we want to see the percent reduction, percent metallization, and also the microstructural behavior, how it evolves once the ammonia is used. The experiments are very simple. Heated to a temperature, desired temperature, holded it for a predefined time, and then cooling under inert atmosphere. The variables are like this. It's all about a single pellet experiment. We want to study very fundamentally what is happening to understand the ammonia reduction. So it was about a single pellet. The average pellet weight, which is typically used in the steel industry, is 3 gram, and the flow rate of overall flow rate of the gas that we used is 200 to 220 milliliter per minute. Experiment set 1, 10% ammonia is introduced, remaining is hydrogen. Experiment set 2, if you crack this 10% ammonia, you get 13.6% hydrogen and 4.5% nitrogen. So that experiment set 2 is nothing but a cracked ammonia condition. So what I am doing, I am cracking the ammonia outside and then sending the mixer to the retort. In the previous case, I am directly sending the ammonia to the retort. Experiment 3 is, I want to compare it with the hydrogen reduction. So I am not using ammonia, I am not using a cracked ammonia. I want to see if I use a hydrogen, how it is. Because there is a lot of discussions going around hydrogen, and now we want a clear-cut comparison that ammonia is better or the hydrogen is better, or a cracked ammonia is better. So that's the reason, that's the question to be addressed. Temperatures, intentionally we selected the high temperatures. We all know that hydrogen reduction is possible at 500 degrees Celsius to 700 degrees Celsius even. But we selected at a high temperature, that is, there is some reason for that. I'll explain due course. The time is given here. And that's the experimental setup we have, a complete gas bank with a controlled mass flow meters, and then to do this. Here you can see the degree of reduction. That's the result. So all three set of experiments are plotted in the graphs temperature wise. You can see at 800 degrees Celsius, the green line is ammonia, which says that reduction through ammonia is poor, but the reduction rate is very less, whereas the hydrogen and the cracked ammonia is comparable. At 120 minutes, it goes up to 80% of degree, reduction degree. And when you increase the temperature to 900, you can see slowly the ammonia is popping up and moving close to the line that is for hydrogen and cracked ammonia. At 1000 degrees Celsius, you can see that is intersecting. The line of the ammonia is intersecting at, after 90 minutes. And then it shows superior reduction compared to cracked ammonia and hydrogen. So that means that there is a process window, there is a temperature, there is a time where ammonia behaves superior than hydrogen. Okay, we all know that hydrogen is a better reducing agent, but there are situations where ammonia can be doing better. Now, you can see here, after reducing the pellets, we collected the pellets and we want to see on the surface any nitride has formed or not. So we collected the powders from the surface and then we did XRD, X-ray diffraction analysis. These are all the pellets of 120 minutes reduced at a different temperature, 800, 900 and 1000. And you can see that there are small peaks of nitrides, Fe3N and Fe4N, which is coming up as you increase the temperature, which is completely controversial to the reported literatures. The reported literature says that nitrides will form only at a low temperature. But what we are seeing is increasing the temperature, that increases the nitride peak. That means more the temperature, more the nitride formations. We shocked, we want to see why it is happening so. And to compare, that is the cracked ammonia condition, where the nitrogen is given as a nitrogen, or you can see it as a hydrogen case also. There are no peaks of hydrogen. This confirms clearly that when you use ammonia, there is a small nitride formation. When you don't use ammonia, it can be a cracked ammonia, or it can be only hydrogen, there are no nitride peaks. So that's here shows the scanning electron micrographs. You can see the last one, this is the nitrogen. This is nitrogen and remaining are oxygen, silicon, iron, all these things are there, and the various point analyses are given. Most of the places you can see 85 plus iron is there, that is completely reduced. That is for 900 degrees Celsius surface, and that is 1000 degrees Celsius. As you see that one, if you follow the nitrogen, the intensity of the nitrogen increases from 800, 900, 1000. It is not very clear that what is there, why the nitrogen is more at a high temperature. Just we are confirming with the several characterization methods and tools to see it is really the things is like that or not. And we want to understand at the atomic level. We have a very sophisticated experimental facilities at IIT Hyderabad. This is the atom probe tomography, 6000 LEAP, which is one of the probably US universities also don't have right now. This is such an advanced atom level characterization facilities. You can see the three-dimensional. Can you click there? Oh, it's not happening. It's not moving. Is it moving? Sorry, there is a problem. I think there is a small video probably because of that. No, close the program. Oh, why? Should not be. You can close it and then reopen. Can you just reopen it? Go to this folder. Yes. Yes. Yeah. Sorry for it. Should I come there? Yeah. No.
Because your file is too big, 2 gigabyte.
Oh, okay.
Okay.
Is it opening?
Yeah. Jadi teman-teman, salah satu strategi ketika ada yang gangguan teknis dikasih applause, atau ada yang berbicara lagi grogi dikasih applause itu sebagai courage, oke? Give applause again. Woo!
Let us see that. Yeah. Excellent. Sorry for the problem with the laptop. Yeah. Yes. So this is the elemental distribution at atomic level for different elements. You can see it confirms that there is a formation of iron nitride and iron Fe3N and Fe4N. And what you can see, that is not distributed homogeneously. Interestingly, that is at one particular interface, there is a concentration of nitride is high. And what is that interface? If you see, there is a SiO2. Silica is basically one of the gang minerals present in the pellet. So what is happening is, when I increase the temperature, the iron oxide reduction is happening, iron is forming, and ammonia is there. So nitrogen, when it dissociates, this nitrogen gets into the iron matrix. So there is no nitride formation. What is happening is actually nitrogen dissolving. Because at 900 degrees Celsius and 1000 degrees Celsius, iron exists in the form of gamma iron. So the gamma iron is like, iron FCC structure, and the FCC takes a lot of nitrogen into it. Oh, I am pressing. Oh, sorry. Okay, so because of that, so at 900 and 1000 degrees Celsius, you are having nitrogen is going into as a dissolution state, and when the pellet is cooled, during pellet cooling, what is happening is, the dissolved nitrogen is precipitating as a nitride. So basically, our temperature and the time conditions, you can see that distribution in a 3-dimensional view. So, and this is the line analysis you can see. So what we want to confirm here is, our temperature and the time conditions are not actually for nitride formation, whereas it is for nitrogen dissolution, and followed by nitride precipitation during the cooling period. which we have confirmed. You can one more interesting observation you can see where, at the pellet surface. These are all reduced iron particles, and you can see a good distance between. There's a clearly visible interparticle distance between the particles when the ammonia is used as a reductant. You can also see there are a lot of pores and small dimples on the surfaces when the ammonia is used as a reductant. So this aids in diffusion of hydrogen inwards and H2O outwards. So the kinetics of reduction is high when the ammonia is used. And you can see this is the case when the hydrogen is used. When the hydrogen is used, you see the particles are almost diffused, and there is no interparticle diffusion. Interparticle spaces are visible. So this clearly confirms that, and you can see the surfaces are very smooth. So there are no defects or cracks on the surface of the particles, which confirms that diffusion of hydrogen inwards and H2O outwards is hindering when the hydrogen is used as a reductant. Why it is happening? The main reason is at the surface, ammonia is undergoing decomposition. The decomposition reaction of ammonia is an endothermic reaction. So the surface is not at 900 degrees Celsius, it is relatively at the lower temperature. So when the pellet surface is at the low temperature, the sintering of the particle is not happening properly. So when the sintering is not happening properly, you are left out with a good amount of pores and the clearly visible interparticle spaces, which aid further, better reduction. So that is the ultimate conclusion. I'll just rush through the kinetics. We all know this shrinking core model when only iron oxide reduction is present, but this is the case when the ammonia is present. There are multiple reactions that comes into picture. The traditional shrinking core model will not applicable. There are several steps involved. So we have developed all these kinetic expressions for the different cases when the nitrate layer is constant, when the nitrate layer is growing, and when the nitrate layer is not present at all. All these expressions are given. This is like, 50 to 60 pages of derivation. I just showed the last thing. And kinetically, you can see for the ammonia case, we get activation energy of 34 kilojoule per mole, which corresponds to reaction control. And the reaction is what at the surface is the ammonia decomposition. Ammonia decomposition becomes the rate controlling step, whereas in case of cracked ammonia, it becomes the diffusion of hydrogen. So the mechanistically, what we want to see is, what we want to convey is, at the surface where the ammonia cracking is take place, there is an endothermic thing. The heat is absorbed and the sintering of the particle is not happening. Because of the sintering of the particle is not so much happening, the hydrogen diffusion is easily possible. So the reduction of iron oxide when you use ammonia is better than hydrogen at higher temperature and higher time. And this is the comparison of the activation energy with the reported literatures for ammonia, and our case stands at here. This is for ammonia and this is for cracked ammonia. Thank you all. I intentionally didn't keep any conclusion slide because this subject cannot be concluded. It will keep going and then we will be hunting. And we are coming up with the 10 kg scale of production from single pellet to 1 pellet to 1 kg thing. Probably in the next sometime in the symposium or the conference I will be able to present. Thank you all.
Okay, thank you. That's a very nice presentation. And we still have 5 minutes for Q&A. If there's any question from the audience, please raise your hand. Maybe while you are thinking about the question, I can give you some, I have one question, which is, it's very interesting that the ammonia cracking is endothermic, yeah? So on the surface of the particle, the temperature may not be that high. Is it possible that the poor reduction ability of NH3 compared with the hydrogen at certain temperature is not actually due to the lowering in actual temperature of the process?
So at the low temperature, when we use ammonia as a reductant, what we saw is the reduction percentage is not that much high. It reaches maximum to 80%. That shows that the decomposition of ammonia is incomplete at the surface because it takes a lot of heat from the pellet surface. So the pellet is actually not at 800 degrees Celsius. It may be at 750 or 700 degrees Celsius, where the complete decomposition of ammonia is not taking place. Or else, there is another way is also possible, which we don't have right now the proof, so we did not show that. The ammonia directly get into react with iron oxide, which can form N2 and H2O. Instead of dissociation, the ammonia can directly involved in the reduction, which may be possible at the low temperature, and we don't have exact result on that or proof, so we don't want to claim that is what happening. But at the higher temperature, definitely the temperature is very high, thermal cracking of ammonia has to happen, and after 50% of reduction, the surface will be mostly of a fresh iron, and this fresh iron will act as a catalyst for ammonia cracking. So all atmosphere or the conditions are conducive for ammonia cracking at high temperature. So beyond 90 minutes, if you see, the peak is intersecting. So the reason is more ammonia decomposition and more reduction is taking place. At the same time, the sintering is not happening, the hydrogen can easily diffuse.
Okay, thank you very much. So one more question, please. If you have one more question from the audience. Oh, yeah.
Thank you for the opportunity, Pak Taufik. Very nice presentation, because our research is also about ammonia, but not for iron ore, but for nickel ore. And the reaction pathway for us is still confusing. And how to prove that the ammonia will be cracked first, or the ammonia will be directly reduce the iron oxide and nickel oxide to form iron and nickel solution will be happen. This is very difficult to see. Do you have suggestion, for example, special experimental setup or method to differentiate, to distinguish the pathway of the reaction?
Yeah, so the one way is we did the experiment in such a way, ammonia and cracked ammonia conditions, so we could see there is a nitrate formation at the ammonia surface. So that clearly shows that ammonia is decomposing at high temperature. When the decomposition is taking place, then only the nitrogen is released and the nitride can form. But when you give the nitrogen as along with the cracked ammonia, the nitrate is not forming. So what is clear from this experimentation is there is a nitrate formation when you make a ammonia as a reductant. Now, coming back to the other point that what we are discussing, what is the reaction mechanism, whether the ammonia can directly involve or after cracking it is involved. So that can be confirmed. I think what I feel is we should connect our experimental setup with the gas analyzer, the exit gas analyzer. What we did is we right now we don't have exit gas analyzer to see what is the ammonia coming out, left out with reduction or completely reduction, ppm of ammonia, whatever it is. So maybe if we connect our off gas with the gas analyzer and then we continuously measure the percentage of ammonia that is coming, then we may able to make a comment that at a low temperature more ammonia is coming without dissociation. At high temperature, no. In fact, we took a samples in balloons and then we checked it. At high temperature, there is not even a single ppm of ammonia is coming. Everything is cracking. At low temperature, probably we have to check that with exit gas analysis coupled experiments. Yeah.
Okay. Yeah. Thank you very much for your answers, and let's give another applause for Dr.
Thank you for the organizers.
Okay. Now we move on to the next speaker. The next speaker is Mr. Bima Satriatama from Swinburne University of Technology. So currently he's a PhD candidate in the high temperature extractive metallurgy at Swinburne University of Technology. So Bima finished his bachelor and master degree from Institut Teknologi Bandung from our lab, pyrometallurgical lab. And today he will present about simultaneous silicon production and purification via Swin H2 in-flight hydrogen plasma. Bima, can you hear us?
Yes, I can hear you loud and clear.
Okay. Okay, so you have 20 minutes for presentation, and then later we continue with Q&A for 5 minutes. So over to you, Bima. Yeah. Let's give another applause for Bima.
Thank you for a very nice introduction. My name is Bima. First off, I'm really apologize I couldn't present there in person. But it is very nice to become a speaker, as I once also studied at ITB, especially mentored by Yadi and Dr. Taufik. But I'm currently a final year PhD student at Swinburne University of Technology here in Melbourne, Australia. So in my PhD, I'm studying several routes to make a green silicon production. So I'm exploring the use of molecular hydrogen, hydrogen plasma, which we will cover today, and also metallothermic. And the title of this talk will be simultaneous silicon production and purification with in-flight hydrogen plasma. So in Swinburne, we called our reactor Swin H2+. So I would like to thank my co-authors and the institutions that helped me, including Swinburne's, ISARO, and our industrial partner, Upala. So we are studying silicon because it is a critical metal across many countries, including US, Europe, Australia, India, UK, so on and so forth. And Indonesia, interestingly, not classified the silicon metal, but the quartz itself as a critical mineral. And in terms of the application, silicon is currently used for aluminum alloys in the steel industry as ferrosilicon and also in chemicals as silicones. But in the future, the demand will be more of a high-end application needing higher purity of silicons, including PV cells, semiconductors, and also lithium-ion battery anode. And in terms of PV cells, so IEA, or International Energy Agency, stated that the PV capacity needs to quadruple by 2030 to be on track on the roadmap of net zero emissions by 2050. And also in the term of battery anode, the growth of silicon could be up to 460 times by 2040. So we know in the future that the silicon demand will increase, especially with these applications. However, the production of silicon currently heavily relied on carbothermic because the process itself currently produces 4.7 kilogram of CO2 per kilogram of silicon. And in the submerged arc furnace, which is the furnace to make silicon, the temperature can exceed to 2000 degrees, and the temperature difference in the furnace can promote different reaction. So at lower temperature, we producing silicon carbide, and above 1800, we making SiO gas, and then the silicon making reaction happens above 2000 degrees, where the SiO gas reacts with silicon carbide, and another silicon making reaction is where we can condense SiO gas into silicon. And this reaction will be very relevant when we talk about our results later. So because of the demand will increase, so we need to trying to find a greener way to make silicon. And I believe all in the audience already familiar with this Ellingham diagram. So basically what I want to say is that we couldn't produce silicon with molecular hydrogen, but if we have this hydrogen as a hydrogen plasma species, it could be H or H+, we may have a chance to make silicon because the thermodynamic significantly change. So in this experiment, we want to answer the question, can it actually work in practice? So these are some few insights on hydrogen plasma for extractive metallurgy. So I've taken this from our review paper in 2024. So by definition, hydrogen plasma is a higher state of hydrogen. It could be excited, atomic, or ionized. And this can reduce a broader range of oxides, as you can see in the previous figures. And in terms of kinetics, it can lower activation energy. And if we talk about hydrogen plasma, we must acknowledge the presence of argon because it can stabilize the plasma. And research show that increasing the concentration of hydrogen can increase the voltage drop and eventually the power input. And we need energy to make the plasma. And basically, generally, it comes from electric arc or microwave radiation. And hydrogen plasma can not only reduce oxides, but it can also refine metals because the reactiveness of hydrogen plasma can vaporize the impurities or making hydrides based on the impurities. And then we ask ourselves, can we then use this hydrogen plasma for silicon production, considering we are dealing with stable oxides, energy-intensive process, and also high purity requirements in the silicon metal? And to the best of our knowledge, we haven't seen any silicon formation from its oxide from hydrogen plasma being demonstrated. So that's why in Swinburne, we developed this Swin H2 Plus in-flight reactor, hydrogen plasma reactor. It consists of a stainless steel tube mounted on an aluminum frame. And at the top, we have the plasma gun that connected to a 3D printed copper shroud. And then we have a bottom mesh collector where we collect the powder. And the important features on this reactor is that we have a huge temperature difference with the plasma that is very high in temperature and the shroud and the sidewall that is very low. And if we zoom in at the top, we basically both water cooled the plasma gun and the copper shroud, and the plasma arc are generated between this cathode and also this anode. And that's where we inject the gas and the powder. We also inject argon on the side from the shroud. So this is to make a sleeve or kind of to shield the particle going out of the plasma. And then we also use this G4 powder feeder to inject our powder to equip with the load cell so we can regulate powder feed rate. And these are the general operating conditions that we use. So we can only go up to 10% of hydrogen due to the limitation of the plasma gun. And we usually run for about 2 minutes. And 2 minutes, not necessarily the reaction time, because the reaction time happens very quickly at the tip of the plasma gun. And these talks will be having two parts. First, where we try using pure quartz, and then second one where we using biogenic silica. We'll cover that later. And then both will be used hydrogen plasma in under short time and low hydrogen concentration. And these are the products if you're using pure quartz. So basically, we collect the sample from 3 areas, from the shroud, the sidewall, and the bottom mesh. And if we analyze this in bulk with XRD, we found that we're producing a trace amount of silicon on the sidewall. And we consider this a novel finding because we don't really put any carbon in the system of the process. And if we look on the microscope, we see a progression of silica reduction from initial silica that contain 47% of silicon up to 64% of silica, which are a stoichiometric SiO. But unfortunately, we haven't found any silicon yet, because it could be that the powder that is deposited on the sidewall are very fine and it's hard to find it locally. So the challenges are obviously we have extremely short plasma and silica interaction time with a very limited hydrogen. So this could be probably tackled with patch or counter, which ITB I think also have. But obviously with patch, we have like the benefit of in-flight, which are continuous, relate to scalability. We don't have powder products or natural rapid quenching effect that I mentioned, and could also have less issue with reactor overheating. And we may, in the process, produce a significant SiO gas, but we couldn't capture it to make the silicon. So we're asking ourselves, can we then introduce carbon in the system in a clever way without compromising the net zero goal? That's why we try rice hulls. So rice hulls is a byproduct of rice. It's about 20 to 30%. And the interesting part is that intrinsically, rice hulls contain silica and carbon. So we might have a self-reducing feedstock that can produce silicon. And it is very relevant in the symposium because India and Indonesia both are the top producer of rice. So basically, we produce rice hulls a lot. And globally, we produce around 164 million tons rice hulls annually, and this can translate to 15 million tons potential of silicon, which already higher than the current production rate of silicon. However, it's not optimally used because mostly it's burned or landfill. So our industrial partner, Upala, sent us 5 types of rice hulls. This is taken along their supply chains of making pure amorphous silica from rice hulls. So the first is raw hulls, where we have silica and carbon, but still high in LOI and impurity, especially potassium and calcium. And then if we leach that rice hulls, we have lower in potassium and calcium. But if we want to lower the LOI, we need to pyrolyze it. So if we pyrolyze the rice hull 1, we got rice hulls 3, higher in silica and carbon, but still have a high potassium and calcium. But if we want to have the best of the both worlds, we can pyrolyze the rice hull 2 to get rice hull 4. So however, we cannot try this directly into our reactor because based on our Fex's thermodynamic calculation, we need to optimize the carbon to silica ratio. So our rice hulls currently have too high of this ratio, meaning we only produce silicon carbide. If we have too low, we don't have enough silicon carbide to make the SiO gas, which is a hub to make silicon. So the window to make silicon is 0.25 and 0.45, with 0.3 being the optimum because it can produce the most silicon. And that's where we're going to do on our experiments. And I want to be very clear as well, is that adjusting this ratio is done by adding silica. So we did by adding pure quartz or by adding rice hulls 5, the amorphous silica, and not adding additional carbon. So in a way, we're diluting the carbon that is already there in the rice hulls. So these are all the products. Again, we collected from 3 areas, shroud, sidewall, and mesh. We tried several feedstock of rice hulls. And based on the bulk analysis with XRD, we found a significant production of silicon, especially in the rice hulls after pyrolysis, rice hull 3 and rice hull 4. Rice hulls before pyrolysis, RS3, only produce a trace amount of silicon. We also have a small peak of silicon carbide, which we are expecting it. And now the question is that, does hydrogen plasma have a role on this, or is it all because of the carbon? So we tried a different hydrogen concentration, 2 and 10%, and we found that in 10% we produce a stronger peak of silicon, meaning we produce more silicon. And then the important part is that hydrogen plasma can simultaneously separate impurities. So we found this throughout our samples that there is a high calcia phase segregated away from the main matrix body of the samples into the outer shell. This is related to the vapor pressure of these impurities being higher than the silicon, meaning they are easily volatilized compared to the metal of the silicon. And now these are the images of the silicon. We can find it throughout the samples. So the main matrix is the melted silica with a lot of pores. So as you can see, all these pores could be translated to the gas channel that is formed because of the SiO gas that is formed in the process. And interestingly, the silicon particle is also associated with silicon carbide. So as you can see, this tiny and thin faces is silicon carbide surrounding the silicon phase. And also the silicon is associated with partially reduced silica phase. As you can see, this globular silicon are surrounded by a strongly reduced silica phase. So in a way, this tells us about the reaction mechanism where it needs to be past the silicon carbide and partially reduce silica phase, not necessarily that the hydrogen plasma can directly reduce the silica into silicon metal in one step. We also perform EBSD. So EBSD is electron backscatter diffraction. So it uses a diffraction mechanism just like XRD, but in microscopic level. So basically what we get is a Kikuchi pattern. It's a basic electron diffraction that is very characteristic to certain crystal. And the software of the EBSD can index that pattern into phases. So basically we can sure know that the particle that we made is crystalline silicon and crystalline silicon carbide. It's not just a silicon-rich phases that we found in the EDS. And we get the orientation map as well, showing different orientation of the crystallography. So basically, this irregular silicon have different domains, and we found that the boundaries is 60 degrees, and this is related to twinning in silicon. So different grain is just a symmetrical grain and not just a random grain formation. And if we look at the more globular silicon phase, it shows a more dominant orientation, showing solidification can come from one main droplet or nucleus. So basically, EBSD confirms the index crystalline silicon and silicon carbide, supporting XRD and SEM-ETS evidence previously. So in conclusion, SWIN H2 Plus is an in-flight hydrogen plasma. We studied different silica feedstock under short residence time and 10% hydrogen. So for quartz experiment, it provides proof of concept of silicon formation, but only at trace level, highlighting the challenge of SiO gas loss and incomplete reduction. Pyrolyzed rice hulls strongly enhance the silicon formation when we adjust the ratio of carbon and silica into 0.3 by adding silica. And then we perform XRD, SEM-ETS, and EBSD to confirm that we form silicon carbide and also partially reduced silica. And all in all, hydrogen plasma contributes to heat generation, activated hydrogen species, and impurity volatilization to enable simultaneous silicon production and purification. Before I wrap up, actually, since I cannot come there in person, I have a bonus slide for the audience. So this is to spark more interest. So in Swinburne, we also tried other green silicon production. This one is one-step metallothermic silicon production and select separation. So in Swinburne, we tried to find different slag candidates where we optimize the viscosity, the density difference, the silicon purity, the slag amount that we produce to have a process where we can making silicon and separate it from the slag in one go. So in particular, I want to explain a bit about this PV arrangement. So we touched base on PV earlier. So basically, PV will have end of life, and it predicts that by 2050, the waste will be 80 million tons. And this PV, we have this glass, which are silica-based and also aluminum frame. So we can use this as an aluminothermic to make silicon. So in a way, improve the circular economy. So we have this feedstock in Swinburne, and the composition of the PV glass is 74% silica with high sodium oxide, calcium, and magnesia. So it is very low grade silica, not like quartz, which have 98, 99% silica, but we tried with our preliminary thermodynamic analysis, and we actually can form silicon, which are very big as well. So at 1600 degree for 2 hours, we can form 2 millimeters of silicon, and this is confirmed by the EDS. It's very pure, and you can also see at the right that silicon is clearly separated from the slag. And you will get more detail on this on upcoming 3-part series. So there you have it. We will obviously publish all the results here in a paper, but you can enjoy our previous paper before. You can contact me or my supervisor Akbar Ramdhani if you know more or possible collaboration in the future. Thank you very much.
Okay, thank you very much, Bima. Yeah, so we open for the Q&A session. Any question from the audience? Please raise your hand. Panji, where is Panji? Oh, yeah, Dr. Ashok.
Hi, Bima. That's an excellent presentation. In one slide, you told the plasma usage of hydrogen that provides heat for reduction, right? In the conclusion slide also. Can you throw some light on it? How heat is given here because of hydrogen?
Yes,
plasma?
so basically, as I think Professor Zul as well already give us something, is that plasma is very activated and it is high temperature locally. So we also know basically to make the plasma we need a very high temperature, and that is provided by the basically different voltages on the cathode and anode. So locally, plasma contains very high energy and high temperature, and we need this in silicon production because, as we know, silicon produce reaction can happens at above 2000 degree, which I believe in a lab scale is hard to maintain this kind of temperature using resistive furnace or even induction furnace. Maybe I'm wrong, but yeah, plasma in a way make this reaction happens locally to reach this temperature, and obviously we just need to regulate the reaction, the chemistry before going into that kind of temperature to make silicon.
Did you do any experiment without hydrogen plasma, like the carbon and volatile matter that are present in the rice husk, alone as a reductant? Did you do any experiment?
We haven't as of today, but we will try that using molecular hydrogen with also rice hulls. We also interested because we tried using molecular hydrogen, and we found that, so I have a slide actually. So increasing temperature and time, we can see the mass changes of silica. So we expect this is coming from SiO gas formation, and you can see this is linear, very linear, meaning that it doesn't have a stagnant mass change because it keeps consuming the hydrogen to make the SiO gas, and we want to use rice hulls to actually see if the SiO gas that is produced can also react with the carbon inside and produce silicon as well.
Okay, yeah, good work. Thank you.
Thank you very much.
Okay, so we are running out of time, so we can only accommodate for one question. Let's give a big applause for Bima Satriatama. Okay, the next speaker is Dr. Fahriza Abdul. I would like to invite Dr. Fahriza Abdul to come to the podium. Let me give you a brief introduction of Dr. Fahriza Abdul. So he did his bachelor and master degree at Department of Materials and Metallurgical Engineering at the Faculty of Industrial Technology and System Engineering in Institut Teknologi 10 November. And he finished his PhD in Tohoku University, and currently He is also a head of undergraduate program at the Department of Materials and Metallurgical Engineering. So, Dr. Fariza Abdul, you have 20 minutes for presentation, and we will follow up with Q&A, and the time is yours. Yeah. Let's give a big applause for Dr. Fariza Abdul.
Okay, thank you so much. Hello, everyone. Good morning. Thank you so much for the opportunity. It's an honor for me to present our research result at ITS Surabaya. And for today, for this opportunity, we will present about the ammonia gas reduction of lateritic nickel ore to produce ferronickel production. And here is my team and our collaborator, not only from ITS, but several institutions. Next, okay, next. And here is our laboratory at Surabaya. Yeah. As you know, Surabaya is located at East Java. So Bandung is West Java, Surabaya is East Java. And in our laboratory, there are several members of professors, Professor Sungging and the others. And our research focus on decarbonization, both for the main process and also CO2 capture. And we also conduct biohydrometallurgy for the other professors, and we have several collaborators and partnership currently. Next. And before I continue my presentation, I have a question. Do we believe with climate change? Yes? Do we believe with climate change? Do we believe with global warming? Yes, also. Why? We cannot see it. Yeah. As analogy, do we believe with oxygen? Of course, we believe. We breathing every day using oxygen in the air. Okay? Because of oxygen can be measured. There's also global warming. Yeah? Global warming also can be measured. Increasing temperature since pre-industrial level, after industrial level until now is very high. And the limitation is 2 degrees C. Above that level, what happened? Many disasters will happen. So climate change, global warming should be controlled. We should maintain our heating temperature of our Earth not exceeding 2 degrees C. And here is the global warming potential. So the IPCC, Intergovernmental Panel on Climate Change, they define to compare several gases with the heating of our Earth temperature. For example, CO2 is 1. The value of CO2 is 1 for the GWP. The CH4 is 28. The N2O is 273. That means CH4 28 times make our Earth temperature hotter than CO2. N2O 200 more hotter than the CO2. So by doing this, the IPCC can distinguish, can compare which gas will have a dramatic effect to the global warming. And here is the figure. The y-axis is the primary energy demand. The x-axis is global warming potential for non-ferrous. If we compare it with the steel, so we can know that the ferronickel production is the most energy intensive and CO2 emission intensive industry. It's also already noted by Professor Zul in his presentation. So it means why ferronickel can make the processing of laterite nickel ore have high energy requirement, because the low nickel content in natural ore results in high energy demand, high energy for production, and make it also has high global warming potential. Next. Okay, and here is the graph I got from the booklet from the ASDM, Ministry of Energy and Natural Resource of Indonesia. we can see clearly that now Indonesia nickel reserve, high grade of nickel reserve, that has high grade of nickel above 1.5% is limited. Yeah? It means, yeah, at current production rate, the high grade of nickel ore in Indonesia will be depleted in 14 years. Yeah? Based on 2020-30 data, ferronickel production in Indonesia is around 500 tons. Thus, by simple calculation, rough calculation, we can estimate that the global warming potential or CO2 emission is 27.6 million ton equivalent per ton of nickel product, the total. And if we compare it with the cement industry, it's even higher than cement industry. So all effort to reduce CO2 emission in the ferronickel sector are urgent before our nickel reserve will be depleted. And here is the data why we choose ammonia. We got the data from the World Bank, and it notes the export-import activity for several sectors, including ammonia and hydrogen for Indonesia. Here is the data for ammonia. Since 2019 until 2023, we can see we have positive net export of ammonia gas. In the other hand, for hydrogen is inverse. Yeah, we still have import larger than export for hydrogen. So it can be rough conclusion that our ammonia plant in our country is already established. Yeah. So our research here, we have two main research in our laboratory. The first one is the decarbonization in the main process. We choose ammonia because of the background. And the second one is decarbonization after the main process by CO2 capture using ferronickel slag. And here is the thermodynamic, basic thermodynamic for several reaction, possible reaction if we react ammonia with lateritic nickel ore, we can see that the iron oxide reduction using ammonia is feasible, okay? Nickel oxide reduction with ammonia is also feasible. And here is the thermodynamical simulation. We conduct it using FACSAGE software, and we can see the solution of ferronickel can be formed at around 500 until 900 degrees C. So we choose this range of temperature between 5 until 900 degrees C. And here is the method we use. We use tube furnace, and we put the lateritic nickel ore sample in the combustion boat there, and then we flow the nitrogen for purging first, and then switch to ammonia gas and hold several times. And then we also capture the excess of ammonia using a gas washing bottle, and we fill it with diluted sulfuric acid. The temperature in this research ranges from 5 until 900 times 30 until 120 minutes. The flow rate of ammonia is fixed, 0.6 liter per minute, and also at several experiments, we also use sodium sulfate for the additive. And the composition of our nickel ore is 1.3% of nickel and so on. And here is the result of our experiment. This graph shows that even at 500 degrees C, we can have some reduction degree. Even the reduction degree is not so high. By increasing the temperature and prolong the time, we can get better degree of reduction. And the XRD spectra after reduction also shows that the ferronickel phase peak is formed. And it is also confirmed that the ferronickel reduction is successfully done using ammonia gas. And here is some kinetic. We use several kinetic model chemical reaction, 3D diffusion, 3D growth of product nuclei based on Aframi-Erofif equation, and so on. And based on the fitting of the experimental data to this equation, we can know that the most close mechanism is 3D growth of product nuclei, because we can clearly see that nuclear formation become larger and larger if we prolong the time. And the apparent rate constant will be like this one. And here is the other research result, but in this research, we add some additive using sodium sulfate. Using sodium sulfate range from 0 until 20% by mass, and we can see if we add 15% of sodium sulfate, the product will be melted. Yeah, and the XRD also confirmed that ferronickel peak is also formed, and after smelting, after the reduction product obtained and then continue to smelting using electric furnace, we can get some metal there. So we can prove that ferronickel metal can be produced. And here is the framework to calculate the decreasing of the CO2 emission we use. So we try to compare when we use ammonia as reduction gas with the conventional process, which is use ultra-high coal. And here is the result. And we can clearly see that in the scenario 1, when we conduct survey to the industry, the global warming potential of rotary kiln and electric furnace only, not all of the plant, is around 13 ton CO2 per ton of ferronickel produced. By using scenario 2, by using ammonia, the global warming potential can be reduced significantly, only 4.82 ton CO2 per ton of ferronickel produced. And our collaborator also conduct some machine learning to use artificial intelligence and data science to enhance and to speed up our research result. We study using machine learning. And machine learning for reduction of laterite nickel ore is not new. There are several research before our publication, but in this publication, they don't predict and don't study the influence of several feature or process variable. And here is the result when we try to study the process variable such as temperature, time, flow rate of ammonia gas, the ore amount, additive amount to the reduction degree as the target or response in this research. We can see that temperature and time is the most influential variable process for reduction degree. And we also compare, not using machine learning, we use simple regression. We also can predict it, but the R square here is not so high. But when we using machine learning, the R square can increase because in the machine learning, we use non-linear equation, not linear regression. Based on this one, we use 4 algorithm, random forest, PLS, RLSFR, and so on. And RFR, or random forest, perform the highest performance for predicting the reduction degree, both for testing and also training the data. And here is when we try to validate, to make a validation for our model, we can see that the R square is very close to 1, 0.94, and the testing is even higher, 0.97. And here is the SHP, Shapley additive explanation of the model from our machine learning. We can see that the temperature can increase the degree of reduction, time also, additive amount also, but for the ore amount and flow rate can decrease the reduction degree. So the flow rate cannot be so fast. We should control it, and there is a maximum flow rate of ammonia we use in experiment. And here is the predicted reduction degree. Our data set is only 20, but by using the machine learning, data science, we can predict for more condition of experiment of the ammonia gas reduction of lateritic nickel ore. And we can clearly see here, the time should be more than 3 hours, and then the flow rate also should maintain in lower flow rate, temperature should be high. And the future plan is still going because I don't conclude anything. Same like Dr. Ashok, this research still running. Detailed study of the ammonia reduction reaction mechanism will be conducted, primarily to investigate the reaction pathway, because we're not sure the reduction of nickel oxide in the lateritic nickel ore and iron oxide in the lateritic nickel ore is done by crack ammonia or directly with ammonia. It's not concluded until now. The potential for NOx formation will be studied because even we purge with nitrogen, some pores in the lateritic nickel ore contain some oxygen, and the oxygen there in the pores, micropore, will make NOx can be formed. Then the magnetic separation process following reduction will be studied if the scenario is not smelting using electric furnace, but separated physically by magnetic separation. Then experiment using simulated gas, approximating rotary kiln condition, because in rotary kiln condition there is some burner. They burn or combust the fuel, so the CO2 will be high, maybe a little bit oxidative, and the ammonia reducing performance should be different. So using simulated gas will be important. Then other selective reduction agent will be studied because sodium sulfate is also have some price, not so high, but it can increase the operational cost. So we try to use waste gypsum for the next research. Okay, thank you so much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Dr. Fahreza. Yeah, we have plenty of time for questions. Any questions from the audience here or maybe in Australia also? If you're still listening to us, you can also ask questions. Yeah. Okay, one from the audience.
Okay, good morning, Mr. Fareza. I'm sorry, I just forget your name. First, let me introduce myself. My name is Gabriela, and I'm a final year student in ITB. And I want to ask about the composition of the nickel supply that you use in the experiment. First is, what was the initial composition of the ore used in this study? Because based on the presented XRD result, the nickel peaks appear to be more dominant than the iron metallic peaks. Does it indicate that the iron was not completely reduced? And the second question is, why was the 3D diffusion model not used for the 3D diffusion model, especially gender model, not used for the kinetic fitting in this study?
Okay,
Thank you.
Can I answer? Or yes? Okay. For the first question, the nickel lateritic ore we use have 1.3% of nickel and about 29 something for iron. And after reduction, we don't measure the reduction product because we don't separate the metal. Yeah, we just measure the degree of reduction by using the weight difference. And for the second question, why we don't include gender equation, honestly we use gender too, but the R square is not so high, so we exclude it for the calculation. We only choose several model which have best fitting, but not enough because the R square is very close each other. So we need some additional observation by SEM to conclude that the Afram error wave is the main mechanism occur in this study. Thank you.
Okay, one more question. Any more? Okay.
Good afternoon. You have spoken about the application of some kind of model which AI and ML you are using. Now, may I ask you about which kind of multivariate model are you using, one thing. And you have spoken about the R square, which is about 0.8, and later on with the multivariate usage of AI and ML, it has gone as high as 0.97 and all those things. Now, there will be some kind of noises. You know, the R square has 0.8, that may be some reason, there may be some reasons of noise, one thing. How did you reduce those noises? One question. Second question is that, is there any global minima you found out so that the 0.97 value of multivariate AI ML, so that you can confidently tell that your model is correct?
Okay. Okay.
Thank you.
Thank you so much for the first question. For the model we use, yeah, we only use 20 data points, so quite low for machine learning. Yeah. So here is only for the pre-beginning of the machine learning study. So how to increase the accuracy of the model? Of course, to add many data points, and we still running with it. Yeah, we still running the experiment and make the data points become larger. That's the answer, I think. The second, yeah, the second one, maybe in future we can use cross-validation. We can use cross-validation, yeah, and then we can validate with the other external data, not only for our data set, to see the R square difference. Okay, thank you.
Okay, thank you, Dr. Fariza, for the nice presentation, and let's give a big applause for Dr. Fariza. So we come to the conclusion of the plenary session 1. So we now will have a break for 1 hour. So we meet again at 12:28, and please all the guest speakers and also for the invitees, you can have lunch here. Also thank you for listening, and see you again after the break. 12:58, yeah? Okay, thank you very much.
Okay, thank you, Mr. Taufik, for guiding that excellent session. Next, we will now proceed to our next agenda, that is lunch break. For distinguished VIP participant, lunch will be served in the VIP dining area located on the right side of the main entrance. For non-VIP participants, lunch will be served in the dining area located on the right side of the main entrance. We respectfully ask non-VIP participants to enjoy their meals inside the designated venue area. Please note that we will have a 60-minute lunch break, and kindly enjoy your meal, and we look forward to welcoming you back to the next session. Thank you. Okay. Ladies and gentlemen, the lunch break will last for 60 minutes, and we'll be back in 12:28. Thank you. Ladies and gentlemen, our next plenary session will begin in 5 minutes. We kindly invite everyone to make your way back to the hall and take your seat. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and welcome back to Indonesia, India, Australia Symposium on Frontiers in Hydrogen Metallurgy, hosted by Metallurgical Engineering Department, Institut Teknologi Bandung. Ladies and gentlemen, I hope you enjoy your lunch break. And now we will continue with plenary session 3. To lead this session, we invite our moderator, Dr. Argya Majumdar, to come to the stage. To Dr. Argya, the session is now yours.
Good afternoon. Thank you one and all for giving us the opportunity to visit you, Institute of Technology Bandung, and even it is my second time in Indonesia. It's really a privilege for me standing in front of you, Professor Julfi, Professor Taufik, and morning I met Imam Santoro and the other professors and the students. It's really a privilege to be a moderator of the plenary session 2. In fact, this symposium is a connection between India, Indonesia, and Australia. So it's really standing in front of you, it's really a privilege for me. So without much ado, it's difficult time, I understand. All of you have a very good lunch, and after that people generally, go for sleeping. So without sleeping, please hear the professors what they are going to speak. In fact, our first speaker, who is really budding professors and the really working in extractive metallurgy, he has excelled a lot in all over India, and he is really very, very passionate about his work, and I find he is really a fantastic human. Speaking about him is Professor Raj Kumar Dishwar. He has done his BTech from UIET CSJMU Kanpur, and then MTech and PhD from IIT BHU. Also, he is working in extractive metallurgy, and he has been postdoctoral researcher for IIT Madras, University of Olu, and even now he is teaching in IIT ISM Dhanbad. And he has published more than 17 papers, and in under process another 2. Without much time, without much ado, may I call upon Professor Raj Kumar Dishwar, please.
Good afternoon to everyone. So, am I audible? Am I audible or not? Yes or no? No?
Yes, yes.
But I am not able to hear you. So, raise your voice and give me your answer. Am I audible? Okay. So, without going in the detailed introduction, I would like to start my research part. So, please. Before starting my research topic, I would like to discuss a little bit about my institute, currently where I am working. This is IIT ISM Dhanbad. Earlier name was ISM, that is Indian School of Mines. It was established by the Britishers in 1926 on December 9th. So we are celebrating 100th birthday of our institute. So we are having 100 years legacy in the area of mining and metallurgical applications. This is the oldest one department of mining engineering in India. So we are having 18 departments across our institute, including metallurgy and mining. And we are offering different programs, BTech, MTech, MSc, and MBA, after that PhD also in different streams. And we are having different centers also. Basically, currently we are focusing on critical metals. So for that purpose, especially we established one center separate. And there are some centers of industries, just like a Tata Steel and others. So just go to next slide. So I would like to highlight few instruments, especially related to the pyrometallurgy in my lab. We are having very robust system of pyrometallurgy, hydrometallurgy, as well as electrometallurgy in our laboratory. But here I am going to present pyro part, basically, so I am highlighting some instruments. Apart from that, we are having very good laboratories for mineral, as well as for alloy development also. So basically, you can see there are so many furnaces which is having very high temperature operations up to 1800 Celsius with the environment controlled, and we are having two melting units also. You can see in the last line that there is one electric arc furnace which can be used for the plasma arc also, 15 kg capacity, and we are having 2 kg capacity induction melting. We are having gas analyzer also. If we are doing the reduction, this is the setup of TGA. You can see here. We can connect this with this gas analyzer, so we can see the outlet gases, what kind of reduction is going on, what is the efficiency. We can easily calculate the amount of gases conversion for the reduction. There are some other different furnaces. We can use up to 1700-1800 Celsius in controlled way, and this is the microwave reactor. It can be used in the hybrid mode, just like a resistance heating as well as microwave heating. So there is one rolling mill also newly installed in our lab. So this is basically steel technology lab. So now I'm coming to the presentation of research. So basically all of you are familiar with the production, how much amount of steel produced throughout the world, how much amount of steel produced by the India, and what is the position of India in the world. So if we look into this data, we can see clearly. Currently, we are producing around 150 million tons of steel, and our country is targeting to reach this 500 million tons by 2040. It means there is a very large gap in between this, because we are going to become developed from developing country. This is the transition phase in terms of development. So definitely we need some transition in industries also in terms of expansion. So definitely, as you know, steel making industry is very highly carbon emission industries. So definitely, as we will increase the 3 or 4 times production, so it will come into the picture. So at the same time, we have to be very precautious with the increment of the production side. So now I come to the steel mainly. So what are the different raw materials? We have to be very careful about this, because green steel is not just conserved to the carbon emission only, because we are using the different raw materials. So just like iron ore, limestone, and recently we are using DRI also. So especially if we will focus this iron ore and limestone, we are not discussing here carbon basically. We will discuss it later. So during the mining side, if you can see from this data, this is the recent data, and you can see almost 58% iron is converted into fines during the mining before the blast furnace iron making. Only 40-45% is used for the blast furnace. At the same time, if you will see in the mining area of limestone, we are creating almost 50% fines as well as lump. So these fines cannot be directly used. If we will not utilize these fines, definitely we have to put it somewhere. So they will occupy the land, they will come into the contact of air, come in the contamination form in the breathings and etc. It will create a lot of problem. So on the basis of this, I can tell you, if you will look into this, this is the world steel scenario. This pointer is not working. Okay. So from this, you can see, this is the world steel production data. BF rate is mainly used in the worldwide production, means it is dominating, producing 70% steel. Only 30% steel is produced by the electric route. It is electric arc furnace as well as induction melting furnace. But in India, the scenario is quite different. We are producing electric route higher than 50%. Okay, so it means why this route is dominating in India, this is around 58.8%. So the reason behind this, we are having sufficient amount of coal, we are having sufficient of iron ore fines, we are having sufficient limestone fines, so that's why we are able to produce sufficient amount of DRI. So just because of the production of DRI, as you know, India is #1 in the DRI production. So just because of that, we are shifting from this route, BF route, to electric arc furnace route. So now the question is that, in electric arc furnace, we are using the energy in terms of electricity. It is again coming from the thermal power plant, which is run with the help of coal. So is it really helpful? So answer is always like no. We are again producing the higher amount of carbon in the thermal coal plants. So to overcome these issues, how can we minimize carbon consumption? How can we minimize the lime fines storage? How can we minimize the iron ore fines storage? We come to the next kind of technology. In this, basically, I am trying to prepare the flux lime pellets. Flux lime pellet means we are incorporating the lime into the pellet itself before reduction. Generally, we are practicing iron ore pellet making with the help of some binders like a bentonite. So with the help of this use of bentonite, we are creating some amount of silica there. So is it possible to replace this bentonite with other binders? Yes. This lime can be used as a binder as well as flux, because you know in steel making this flux is important in terms of lime. Without lime we cannot produce the steel. So anyhow we need to put the lime into the steel making process at different stages. So what we are doing, we are trying to put this lime in the initial stage, and we are trying to bind the pellets with the help of this one, and then we will endure this and we will harden and then reduction. So I will not go in that much detail of theory. I will come to the research part. So we have taken this iron ore from nearby mines, and we have gone through the different chemical analysis and particle size analysis and different phase analysis. So this is having 92.5% Fe2O3 and 2.94% is SiO2, means this is high grade iron ore. This is the process of making pellets. These are pellets made with the help for the lab scale, but we are having pelletizers also. For higher scale, 2 kg, 5 kg, we are using those pelletizers. So after hardening, what we did? Basically, we have taken different temperature, 1100 to 1200 degrees Celsius for hardening purpose, and the time is varying from 30 to 60 minutes, and basicity varies here 2, 4, 6, 8. So basicity is equal to, here we are considering CaY SiO2 simply. So according to SiO2 is about 3%. So highest lime percentage is about 24-22% here. Okay. So this is crushing strength in graph A. This is the important parameter. So because as you know, for the transport purpose, for charging purpose, and for the traveling time in the kiln and etc., we need to provide some sufficient strength to the pellets. So this is very important parameter. So we have tracked this strength with the help of crushing strength machine, and at the same time porosity is very important in terms of the reduction. If it is not sufficient porous, then it will be very difficult to reduce the pellets. So these are the two important parameters. We have to optimize these two parameters. So for that, we have gone through some experiments and we figure out After 6 basicity, you can see at 1180 degrees Celsius, there are little bit changes in the crushing strength as well as in the porosity. But in case of 1200 degrees Celsius, there is a drastic change after basicity 6. So we have to figure out why this is happening, because you can see here at 6 basicity above at 1200 degrees Celsius, the strength shoot up suddenly and porosity drastically changes. So definitely there is a relation between. So to figure out this, we have gone through the XRD analysis of different samples, and we figure out the formation of different phases, calcium ferrite, dicalcium ferrite in the presence of hematite during the induration. So we can see that dicalcium ferrite is having 142 megapascal strength and calcium ferrite is having 370. So in the cases of 1200 degrees Celsius temperature and 8 basicity, we are forming higher amount of calcium ferrite, this phase. So it can be seen in all the diagrams ABCD, that is the topmost. We are forming higher amount of calcium ferrite phases. This is responsible for the strengthening here. So to support this, we have gone through the microscopy, and in the microscopy, we have chosen 2 samples of 1180 and 1200 degrees Celsius, because before that, samples are not that much interested. So we have to figure out what is exactly happening at that particular temperature. So we have chosen 1180 with respect to 1200 degrees Celsius. So you can see in ABCD all the diagrams, this 4th D, we are having a sintered structure here. In case of A, you can see particles are dispersed at the surface, means they are not coming into the contact with each other, they are not diffusing with each other, means partial fusion is not happening. But in case of D, because the basicity is quite high, here we are using around 24-23% CaO. So when we will look into this phase diagram, this is the point. Here you can see easily lower melting constituent phase is formed. It means at this particular point, when we will reach, the material will start to get melt. When it will start to get melt, it means centering is happening, and it is clearly visible from this particular micrograph. After that, we come to the reduction, and we have chosen 2 different kind of reductant. First one is the carbon, because carbon is abundant in India, and we are running all the industries still on the basis of carbon, coal-based technologies. And there are few industries running on the natural gas-based reduction also, MIDREX. So I am just taking for consideration here carbon and hydrogen. So if you will look into this, in this figure, I would like to explain there is always effect of basicity on the reduction. Because in this figure, once you will see at 900 Celsius, it is clearly visible here. As we increase the basicity, percentage of reduction is increased at particular time or temperature. But as we increase the temperature, when we reach up to 1050, in this case, you can see there is no impact of basicity. Means at lower temperature, this calcium oxide may be act as a catalyst, and it will enhance the reduction of particular sample. But at higher temperature, that reduction mechanism may be shift, so just because of that, it is not having that much role. So if you want to optimize, so definitely we will not go for that one. We can easily optimize at 1000 degrees Celsius in 60 minutes, we are getting the sufficient 90-95% reduction. So why we have to invest the energy at 1000 degrees Celsius? If you will go for the pure pellet, not having the lime, maybe you required 1000 degrees Celsius temperature according to the literature. So by introducing this lime, we can get the desirable percentage of reduction at quite low temperature. So what I am saying, I have again justified it with the help of different techniques. I have taken this XRD plot, which is showing that as we increasing the basicity from 2, 4, 6, 8, different phases evolve, and after that what I did, reduction. After reduction, again I checked what is the changes observed in the phases. You can see from this diagram clearly in 2, 4, 6, 8. In the case of 2 basicity, there is Fe and FeO phases, means this is not fully reduced, FeO is there. In case of 4 basicity, you can see amount of FeO start to increase and FeO is start to decrease. But in case of 6 and 8 basicity, it is completely different. In case of 6 and 8 basicity, you can see there is no FeO, but some amount of free lime is start to evolve. You can see here there are peaks of free lime in the star form. So as we will increase the basicity, amount of reduction will increase in the same condition, as well as we will get some amount of free lime. Because if you will go through the literature and you will figure out, if we will compare the reduction capacity, hematite can be reduced 100%, calcium ferrite can be reduced up to 80%, and dicalcium ferrite is up to 57%. As I explained in my last slide, when we will go for the hardening, as we will increase the basicity, definitely calcium ferrite phase formation will increase. It can be easily reduced up to 80%. That's why we are getting that kind of information. Now you can see it from the micrographs. In the case of this B category, you can see that viscous growth is happening, but in case of COD, viscous not visible, because after increment in the reduction, they got collapsed with each other and the morphology changed completely. This is the data of hydrogen reduction. So I reduced the pellet, which is having 0.4 basicity and crushing strength to 110 kg and porosity is around 10 to 12% here. So there are two different graphs. This is the plot, red color, which is used at 1000 degrees Celsius, and this blue one is at 700 degrees Celsius. Means we are reaching the temperature and reducing the sample for 1 hour. Okay, so in this case we are getting the at high temperature 81% reduction and lower temperature 700 degrees Celsius it is around 67% reduction. But this is the isothermal reduction. So after doing this experiment, I tried something else. I went for the athermal reduction. This is the data of athermal reduction. I started to charge the hydrogen from 500 degrees Celsius and I operated the instrument for 2 hours and it reached the rate of heating is 5 degrees per minute. So you can calculate in 2 hours it will increase around 600 degrees Celsius. So it will reach up to 1100 degrees Celsius, but you can see the reduction is happening up to 60 minutes maximum. After that this line becomes flat at most. It means in 60 minutes we are increasing the 300 degrees Celsius temperature. So it means that whatever the reduction is happening, it happening from 600 to 900 only. And if you will go through the derivation of this one, you can easily calculate the rate of reduction at different time interval for different temperature, because this line indicates just like in 20 minutes, you will reach 100 degrees Celsius. So 500 plus 100, 600. Again, you can increase 100, 100, 100, 100. So by putting this dr by dt, you can easily calculate the percentage of reduction is how much happening, how this rate is going to be changed. So from this data, actually we can say that if we will go for the live conditions, because in any reactors, the temperature is not constant. Temperature is also changing with respect to the height and material is moving continuously. So this is the real life data. And I justified it with the help of this XRD analysis. This first micrograph, the XRD data shows the data of this first sample. So from this data you can see 1 is the iron and 2 is the FeO. So there is a very small peak of FeO, means most of the iron is reduced in the iron and a little bit amount of FeO is visible here, because this is around 90%. So obviously maybe some amount of FeO there. But in case of second and third, this second is for 81% and the third is for the 67%. So in this case you can see as percentage decreases, so amount of this FeO is increasing, and in last one we are getting some amount of Fe3O4 also. So these are the explanation. With the help of XRD you can justify your results. Later on I come to the micrograph. You can see this is the micrograph which is very porous, and you can see there are whisker formations easily can be visible here. This micrograph is almost similar to this one, but this is quite different because this is having 66% reduction, means Fe is low, and obviously here whiskers will form, but in presence of FeO and Fe3O4 other phases are visible, but in these cases this is completely reduced iron oxide into the iron. So now I compared these micrograph in the presence of hydrogen reduction and in the presence of carbon reduction, how they will change it. So from this morphology you can see the growth which is happening here is quite different, and this is very porous structure. So one more thing I would like to highlight. In this case we are using the lime, that is the one lime CaO, but here in this case we are using the egg powder. Whatever the eggs you are eating in the morning in the breakfast, it is having some coverings that is having very high amount of CaCO3. So we crushed it and we mixed it. So obviously this is a calcium carbonate which is having 99% or maybe higher than this. So CaCO3 will dissociate in CaO plus CO2, so that CO2 will take part also in the reduction, and that will create more porosity. So you can see easily this structure and this structure are quite different. So I will take just 5 minutes if it is, because I'm coming to the main things of this one. Whatever the raw material we prepared, we melted this in different furnaces. So this is the data of arc furnace, means arc melting, electric arc. This is simple electric arc in the conditions of air. So what we are doing, we are preparing the different percentage reduction of iron ore, means we have chosen 10 to 80% reduced pellet, and we form the melt pool of pig iron. That pig iron is having very high amount of phosphorus and sulfur. So we are trying to study how they will change the phosphorus and sulfur in the melt pool. So I will not go in the detailed discussion of other elements. I will just show you that in this case there are 30, 50 and 80% reduction of pellet. So we are studying the phosphorus removal. This line is indicating 80% reduced pellet. This line is indicating 30% reduced pellet. 30% reduced means it is having FeO or Fe2O3 or Fe3O4. Because 30% means Fe2O3 just changing into the FeO maximum. Still we are not having high Fe, it may be a little bit. But in case of 80%, most of the Fe2O3 will change into the Fe. We are having very little amount of FeO, Fe2O3 and Fe3O4. So it means source of an oxygen which is coming from the ore itself is changed here, which is affecting the removal of phosphorus. But in the case of sulfur, you can see the trend is just reverse. Because as we all of you know, the oxidizing conditions are essential for the phosphorus removal, and reducing conditions are essential for the sulfur removal. That is, already we have gone through a lot of literature in the books, in the course, that is justified here in my study also. If you look into the induction melting, almost similar behavior is there. I will not go in that much detail of this one. Now I am coming to this particular slide. This is hydrogen plasma smelting reduction. Here what we are doing, we are creating 4 different conditions. First condition, you can see nitrogen plasma. We are not using hydrogen plasma. So when we create the nitrogen plasma, then we see the removal of different impurities, especially phosphorus and sulfur. Sulfur is reduced efficiently, phosphorus is not reduced, because this is the data. This red line means in nitrogen conditions we are creating the environment which is inert, means there is no oxygen. So it will help to increase the sulfur removal. But at the same time, if we are going for heat 2, in heat 2 what we are doing, whatever the lime we put in the pellet, we charging that much amount of lime separately, free lime. Let's suppose in pellet I charge 1 gram. So now what we are doing, we are not charging the pellet there. Now I am directly charging the lime powder 1 gram. So in that condition I am seeing the effect. So in that case, again you can see sulfur is removed up to 92%. Because as we increase the lime, inert atmosphere is there, so that will help to remove the sulfur. Lime is highly basic in nature, so these properties can be easily correlated. And in the case of third heat, what we are doing, we are charging the hydrogen. So in case of hydrogen, you can see we are able to reduce sulfur up to 84%, and at the same time we can remove the Carbon also. I think in last discussion, somebody talking about the carbon can be removed in presence of hydrogen or not. So that can be removed. So basically that is the data. So that kind of hydrogen plasma smelting reduction can help to remove the different impurities from the liquid iron melt. So for more detail, we can discuss it later also because there is a time constraint. So please can you this, can you, this is one video of my experiment. So during my work, I have used this setup. This is the plasma arc melting. So we can inject easily hydrogen into the liquid melt here. We can run this in air conditions also. We can use the nitrogen plasma also. Any kind of gas you want to convert into the plasma, you can use this setup. Okay, so thank you. Thank you from my side.
Thank you, Professor Raj.
So any
it was
questions?
Nice presentation. I think we have one question can be asked by anybody. Any from the audience?
Yes.
Two. Okay, sir, please.
Yeah, thank you, Professor Raj, for a nice talk. My question is about the phosphor removal. In your experiment during hydrogen plasma, so there's no phosphorus removal? Usually, based on the latest result from the other researchers, we have seen that sulfur, phosphorus can be removed simultaneously.
Yeah. Actually, in conditions of hydrogen plasma, you cannot remove phosphorus. But if you will play with the oxygen content, I have that data also, but I didn't present here. If you will play with the plasma conditions as well as oxygen potential in terms of percentage reduction, in that case, up to some extent, we can reduce the phosphorus. So in my research, I figure out we can remove the sulfur up to 60-65%. At the same time, we can remove 30-35% phosphorus also. So again, we have to go for further research in this area to optimize those parameters.
Okay,
but in pure hydrogen conditions, it is not possible.
The same questions. I think the professor in they're in the same line. Thank you, Professor Raj Deshwar. May I ask for a big round of applause for him?
Okay, thank you very much for inviting me. And I would like to say thank from this podium to team which is organizing this. They are making really a very hard effect. I think they are making a lot of effort. So again, I would like to say thank you all.
Thank you. So I'm really privileged to call upon the next speaker, who is Dian Mugni Felicia. I have correctly pronounced your name correctly? Okay.
Yes, correct.
She is in the online. I have pronounced your name correctly?
Yes.
Yes, thank you. She is from Swinburne University of Technology, and she is PhD candidate in mechanical engineering and also assistant professor in materials and metallurgical engineering, Melbourne, Australia. Her work goes with experience across high temperature extractive metallurgy, hydrogen-based oxide reduction, copper containing secondary resources, casting, heat treatment, manufacturing, and material characterizations. Currently, she is doing doctorate work on focuses on reduction of copper oxide and synthetic secondary copper slag using molecular hydrogen and hydrogen plasma with emphasis on copper iron selectivity, reduction kinetics, phase evolution, and microstructural evidence from ACM, BSc, EDS, and XOD. So without much ado, may I call upon Dian Mugni Felicia from Swinburne University. The floor is yours.
Thank you. Can you see my screen?
Not yet.
I think it's There now?
Yes, make it full.
Yes. Sorry. Is it full now?
Yes.
Okay, thank you. Yeah. Good afternoon, Indonesia. I'm Dian Muni Felicia, PhD candidate funded by Swinburne University of Technology, CSIRO, and also Hill CRC. I have a very nice supervisor, gentlemen, Professor Akbar Ramdhani, Professor Suresh Palanisamy, Adjunct Professor Mark Poinsetti, and Dr. Reza Muklis. So today I would like to talk about decarbonization of the secondary copper processing, molecular and plasma hydrogen reduction of secondary copper slag. This work is motivated mainly of two key issues. One, decarbonization, and two is the secondary resource utilization. As we know, copper industry contribute around 0.3% of the global carbon dioxide emission. And secondary copper production already give a significant fraction of the global copper demand. So with that background and then inspired by success story of the hydrogen direct reduction in iron making, SDRGRI, my study is observed whether hydrogen can be used as a clean hydrogen reductant to reduce valuable metal from the secondary copper slag. And here, for the secondary copper smelting and refining, finally we form a final slag that still containing valuable metal such as copper and then also iron and subsilicon. So both a primary copper production and secondary copper production give a challenge, environmental challenge, and also potential. If we do a correct and efficient reduction, so then we will get a valuable metal and we will reduce waste. So maybe it's a bit surprising, but there's not a lot of study regarding the kinetic and also behavior of the copper oxide and also copper slag in the high temperature. So to answer that gap of research, I do several experiments as my PhD research. So it's the solid state copper oxide reduction using a molecular hydrogen, solid state copper slag reduction using a molecular hydrogen, and then continue with the liquid state copper slag reduction using molecular hydrogen. Last but not least is plasma hydrogen reduction of copper slag. So today I will highlight two of my research, solid state copper slag reduction using molecular hydrogen and plasma hydrogen reduction of copper slag. So before we go further to discuss about the result or the experimental part, so first I did slag making. So I'm using a synthetic slag making, and before working with the slag making, so I calculate the factage using ternary diagram, and then it's mentioned here at 1300 degrees Celsius, it's all the powder, my synthetic slag, it's become liquid, it's molten. So then using this baseline, I did the slag making at 1350 degrees Celsius within 1 hour inside the muffle furnace. So then I got this precious slag, and then do a grinding and then milling to reduce the particle size below 38 microns. So this is my copper slag composition. It's an XRF result. And then I also did the thermodynamic modeling using factage as an open system. As we can see here in figure 5, it's a predicted there's a phase evolution of the synthetic copper with the increasing of the hydrogen. So if we zoom in only for the copper and also iron reduction in figure 6, we can see here. So the reduction of the copper should be finished first before the iron starts to reduce. So to justify whether the modeling of this fixage it's correct, so we did the experimental work. So first, I did the solid-state molecular hydrogen reduction of synthetic copper slag. So this is my precious pellet. I made 100 of this. And I'm working with the horizontal tube furnace for its temperature 1000 with a time reduction of 5 up to 25 minutes with a 15% hydrogen, argon, and fluoride 300 milliliters per minute. So if you can see here in figure 9, so this is the result, my SEMEDS result for the reduction solid-state molecular hydrogen. So here, this is 5-minute reduction, and then 15 minutes and 25 minutes. So I did in a several different points. So bottom surface of the specimen, middle cross-section of the specimen, and top surface of the specimen. As we can see here, within 5-minute reduction, it's already formed copper on the top of the specimen. And then within 15 minutes, it's already formed copper on the bottom surface of the specimen and also top surface of the specimen. After 25-minute reduction, then we found iron here. So then, and it's also alloying with the copper. So then, so the prediction of the from the fixage, it's aligned with this result of the experiment. So after I got the result from the solid-state molecular hydrogen reduction experiment, so I know the kinetics of the copper slag in the high temperature in the solid-state reduction, and then I also know the behavior of the copper slag. So then I continue doing the plasma hydrogen, the copper slag reduction using SWIN H2+. So here have several mechanistic insight for the plasma experiment. So hydrogen plasma generate excite H2, atomic hydrogen also ionic H+, and it's make it more reactive than molecular hydrogen. So here, the copper oxide are preferentially reduced, then continue with the iron and also in the stronger plasma exposure. And most silicon oxide here remain stable in the slag. And arc heating promote the particle and droplet melting and rapid gas slag reaction during the short residence times. And plasma expose promote a phase separation, producing copper-rich, iron-rich, and also silicon-bearing metallic region. So this is our SWIN H2+ reactor. And this is the conceptual reaction pathway of my reduction. So I have a copper slag with a certain composition, and then feed it with a plasma hydrogen, and then it's become a molten slag droplet with containing a copper-rich metal, iron, silicon-bearing metallic region, and also residual slag plus off gas. So is it suitable for copper slag, this plasma? Yes, it's promising for selective multi-metal recovery. So best target copper first recovery and then followed by iron and also silicon. But still, we have a key limitation that a stable silicon oxide, a rich network, and a complex slag chemistry. And we got a metal products, copper-rich phase, silicon-bearing iron-rich, or FeCuSe metallic phase plus residual silicate slag. So this experiment, this study is supported by XRF for the initial oxide slag chemistry, and then characterization by SEMEDS after the experiment work. And yeah, for the plasma experiment, I have two stages of the experiment. First stage is the substrate-based plasma hydrogen reduction of the copper slag. As we can see here in the figure 10, we're using a robot to handle the plasma torch, so then plasma torch can make a consistent torch pattern like this in front of the aluminum substrate. And then here in 10C, this is my sample after the coating of the copper slag with the thickness of the coating around 60 microns. So here, this is, I have a video of the experiment where the stage 1 is using SOD around 100 millimeters and plasma torch parameter 52 liters per minute, argon and 1.2 liter per minute hydrogen, 10% hydrogen argon with a 35 up to 45 kilowatt power input at 425 amperes. So after finish the stage 1, we did a characterization, and here I found in several points, I found a copper, molten copper, copper droplet in the aluminum substrate. So A, B, this is cross section, and then C is the surface of the coating. So the presence of the metallic copper ridge in several region, it's indicated early stage of copper metallization during the plasma experiment. And yeah, I found this one, it's only 1 or 2 points where iron and also copper mix together, but still, and also silicon, but still there's oxygen. So it's mean that the reduction is not completely, yeah. And yeah, for your information, this first stage of the substrate experiment, it's conducted to ensure that my powder, my slag powder can be used for the real experiment, the reactor, the plasma reactor experiment. So with the and it's conducted in the open environment. So due to that condition, so the reduction is not maximum. So this is the stage 2 plasma reactor hydrogen reduction of the copper slag, and this is my operating condition. I'm using a very small amount of the feeding copper slag since I have a very limited slag. And then the main research objective here, to assess selective multi-metal recovery from copper slag using the SWIN H2+ in flight plasma reactor under short resistance time and low hydrogen concentration. Only 2 minutes. And yeah, so this is, it's really exciting because I found, so this is a plasma torch and this is our shroud, copper shroud, and we have the reactor here, plasma reactor, and this is powder, the powder collector. So here in the shroud, inside the shroud, I found a droplet of the metal. So this is the reddish one is copper iron metal droplet, while the grayish one is iron copper metal droplet, and this one is slag. So inside the side wall, I mainly found the fine powder of the slag. So I check through the SEMEDS. It's a very fine powder. And then here in the powder collector, I also found a lot of droplet, gray droplet here. And then when I check, actually there's also metal droplet, small metal droplet here. And when I check a cross section, I found a lot of metal inside. So here, from the Stroud plasma reactor result, I got a iron copper silicon metallic phase formation. So as you can see here, I did a 6 EDS point analysis since this is all metallic, all metals. So let's now focus on the spectrum 1 and 3. So 1 and 3, it's a mixture between iron, copper, and iron, silicon, and copper. 1 and 3 with a slightly different composition. So then I'm using the FACSH pseudo binary section with a fixed silicon around 10% to interpreting silicon bearing metallic phases. So here, the spectrum 1 and 3, it lies here. So it should be BCC A2 plus FCC A1. So BCC A2 refer to the iron, and then FCC A1 refer to copper. So I assume that the silicon is become a solid solution with the iron. Now, still using the same figure, but focus on the spectrum 2. Spectrum 2 here, so it's number 2 here. It's mainly iron and silicon, so copper is not detected. So I'm using a binary phase diagram to showing the position of the spectrum 2. So it lies here. So we predict the phase is alpha iron, mainly alpha iron and probably bit of iron Fe3Se. And besides the Stroud plasma reactor result, I also check from the powder collector. So here I have a very nice droplet. So it's a metal droplet. So when I check, it's mainly iron copper. So iron copper and other phase is not detected. So I'm using the FACSH FECU binary phase diagram to plot the spectrum 1 and 3. So here, for the spectrum 1 and 3, it's alpha iron copper with a iron rich. Meanwhile, from the previous figure 16, the spectrum 5 and 6, so it's also iron copper, iron alpha iron plus copper with a copper rich. So that's my result. And I have several key conclusions for this presentation. So molecular hydrogen confirm copper first selective reduction from the synthetic copper slag, and then FACSH support copper-rich metal formation before the reduction of the iron. And plasma hydrogen promote a rapid melting, partial reduction, and phase separation. And STEM EDS confirm we have a copper-rich, iron-rich, and silicon-bearing metallic region after the plasma experiment. So the product metal are multi-phase, not a single homogeneous alloy, and selective multi-metal recovery is promising, but process control remaining critical. So this is my references, and thank you.
Thank you, Professor Felicia. A big round of applause for her. Can we have any questions from your audience? Any questions from the audience? Ashok?
Thank you. That's a nice presentation. What is the yield?
Pardon me?
Yield. How much copper was recovered?
Okay, so can I just stop this? Okay. So yeah, this copper contain, firstly it's around 5%. So then according to my calculation, the copper, it's the metallic copper, it's around 3 point something %. So all the copper is already reduced. So it's 100% reduced.
So, okay, so 100% recovery is there.
Yes.
Okay, one small question.
Yes,
We
yes.
also did similar kind of experiment. We could see that the copper oxide reduced by hydrogen in 600 degrees Celsius itself. But you have maintained 1000 degrees Celsius in your reduction experiment. Why 1000 was required?
Yeah, because the gap of the research is it's a very limited study doing the high temperature reduction of the copper side and also copper slag in the solid state reduction. And it's related with the hydrometallurgy since we're using a high temperature for the reduction. So that's as of my baseline before I'm going further with the liquid state reduction and also plasma reduction.
Thank you.
Thank you.
Any more questions? So, a big round of applause for Professor Felicia. Please. Thank you. The next speaker, I'm really privileged to call upon Professor Taufik Hidayat Dayo. Yes, he is now lecturer of Institute Technology Bandung, the same place where we are standing. In fact, he did his BEam engineering in mining engineering, Institute Technology Bandung, and MPhil from University of Queensland, Australia, and PhD is also from same university. Dr. Hidayat completed his, he is a research fellow at Pyro Search between 2014 until 2018. He joined as a lecturer in Metallurgical Engineering Study Program, Faculty of Mining and Petroleum Engineering in 2019. Some of the research area he is involved include non-ferrous high temperature processing, kinetics of heterogeneous reaction, slag chemistry, and computer coupling of phase diagram and thermochemistry. And he has published more than 80 technical publication in metallurgy area. He is also involved in discussions and the creation of documents related to mineral sector development policies in Indonesia, such as Indonesian grand strategies of nickel, copper, bauxite, tin, gold, silver, coal, and dolomite. The floor is yours.
Thank you very much, Dr. Argia, for the nice introduction. So first, let me clarify, I'm not yet a professor, but aiming to that, hopefully one day I'll become a professor. Thank you very much. So today in this session, I would like to give you some highlights of our recent project. The project is a collaboration between Institute Technology Bandung and Korean Institute of Geoscience and Mineral Resources, or we sometimes call it KIGAM. The project title is Development of Nickel Raw Material Manufacturing Technology from Nickel Oxide based on hydrogen reduction to reduce carbon emission. So today I will highlight several results on the hydrogen reduction of saprolite ore. Initially we would like to do it in the fluidized bed reactor, but we found that I think at the moment we stay just using the fixed bed reactor. So this is the team, me, myself, and also Dr. Taejun Park from KIGAM. Also other researcher, Professor Zulfiadi Zulhan, Imam Santoso, and our colleague Ramadhani Santoso that helped us to do CFD, and our previous and current students such as Aisyah, Gabriela, Gali, and Fierdi. So this work are hard work from our students. Yeah. So just a little bit of background why we need to look at the hydrogen reduction of the nickel ore. We know that smelter development in Indonesia has increased tremendously due to the mandate from the government. The government wants us to do downstreaming of minerals to produce value-added products. And as you can see from the figures, initially we only export nickel ore, but due to that mandate, we start to produce intermediate products such as nickel pig iron, and also stainless steel and MHP. Unfortunately, nickel pig iron contribute significantly to the CO2 emission in the nickel industry. As you can see from your right top figures, it's the highest one. Either you produce nickel pig iron or converting nickel pig iron to nickel matte, it produces, I think, more than 70 tons CO2 equivalent per ton nickel. Therefore, we need to think about something that can replace the carbon-based reductant or fuel. So we think that hydrogen may be one of the options. This is the typical route for producing nickel pig iron. So nickel pig iron is produced through rotary kiln and electric furnace. For some of you that don't know, it's basically using three main equipment, which is rotary dryer, reduction kiln, and arc furnace. And you can see, for example, in the reduction kiln, it uses carbon-based fuel and carbon-based reductant. So we think it's better to change or find some substitute for the carbon-based reductant and fuel, and we think hydrogen is one of the options. So in our experiment later, you will see that we try to use hydrogen for reduction in the condition near the reduction kiln, around 500 to 900. We also perform melting to the reduction product to see if we can separate the metal and the slag as what we can find in the industry. So the use of hydrogen in nickel laterite processing is not something new. It's already been studied before, laboratory scale, bench scale, and also commercially. For example, for the experimental, there are many literature data. One of them is from Chen et al. In 2019. He reduced the nickel ore between 400 to 800 using 15% hydrogen, and you can see how the microstructure, basically we can reduce the iron and nickel from the ore. Also, interestingly, back in 97, 98, there was a trial by Lurgi in Metallurgy, Lurgi in Germany, sorry, did some bench scale test work using 50 millimeter diameter batch type fluidized bed reactor. At that time, they used a mix of hydrogen and CO gas, yeah, and it was at 800 and 1,000. And at that time, they decided to move further. They built a pilot plant and also commercial scale process, which is known as nickel smelting technology. The plant is available in Koniambo Nickel, New Caledonia, but they didn't use hydrogen gas. Instead, they use coal as a reductant, most likely due to operational costs. Coal may be cheaper than, of course, we know cheaper than hydrogen gas. Yeah. Also, from my experience when I did my master in Australia, I visited one time to Yabulu refinery in Australia. They use current process, and in the final part of the process, they reduce nickel oxide to nickel metal using hydrogen, using traveling grade furnace. So hydrogen used in nickel laterite processing is not something new. It's already been done, been proven, but maybe there's some limitation in terms of CapEx and OpEx. So we want to revisit this topic. We've done some thermodynamic evaluation and some targeted experiments. For the thermodynamic evaluation, our student has done this calculation. You can do it using FactSage or just using some data from the textbook. So we try to see how the Gibbs energy change with temperature. The first one is to see whether the mineral inside the nickel ore can decompose, such as magnesium silicate hydrate and also iron oxide hydrate. And as you can see, it's easy to decompose mineral in the nickel ore. Magnesium silicate hydrate become magnesium silicate. Iron oxide hydrate become hematite. Yeah. We also look at the reduction of iron oxide and nickel oxide. Nickel oxide is very easy to be reduced by hydrogen. Just above 100 thermodynamically, it's already can be reduced. But for iron, maybe you have to go higher, above 500 degrees Celsius. So from this information, we proceed further doing experiment. The first one is doing thermogravimetric technique experiment. The second one, we use larger scale, bench scale tests using fixed bed reactor to see if we can perform the hydrogen reduction satisfactorily. So this is how we do the experiment. Basically, we perform some sample preparation, And then before we do reduction in thermogravimetric equipment, we perform calcination at 700. Why we perform calcination? Because we want to see the kinetic only for the reduction. We don't want the weight loss to be affected by the removal of LOI. So that's why we make the mineral stable, already decomposed, and we want to see just the reduction part. So this is the ore that we use. We got this from Sulawesi Island. It's a typical saprolite ore. It has very low nickel, high iron oxide, high magnesium silica. And for this TGA experiment, we prepare the particle size in such a way that we have a very strict particle size distribution between 1 to 25 micron by performing manual grinding. Why we try to do very fine and homogeneous particle size? Because we want to accurately investigate the kinetic. Also, we use a very diluted hydrogen, only 5% hydrogen in nitrogen. Mainly it's because of safety, but if we think about it, sometime in the reactor, in the industrial scale, there may be some pocket of area where hydrogen may be very diluted due to mass transport and other things. Yeah? So that's why we perform in a very diluted hydrogen, just to investigate the kinetic at the most extreme condition. The first test is done non-isothermally by putting the calcine with the weight of 300 milligram, gas flow rate 200 milliliter per minute, and also the heating rate is 10 degree per minute. We done the isothermal, non-isothermal experiment from room temperature to 900. And interestingly, there are two distinct reduction stage. The first one is between 300 to 600. This is mainly because of reduction of nickel oxide and also the transformation of hematite to magnetite and then to wustite. And then from 600 to 1000, this is where the iron start to get reduced from FeO. But we also find there's some competing reaction because FeO can also interact with silica next to it and react, forming ferrolite, and once you form ferrolite, it's very hard to get reduced. So from this non-isothermal experiment, we know that basically reduction takes place significantly above 500. So then we focus on the isothermal reduction experiment at temperature 500 until 900. And we still use the same calcine weight, same gas flow rate, and then interestingly that the initial reduction degree increased with temperature, and also interestingly that at 500 and 600 the reduction is limited. You cannot go above 60%. And also if you do experiment longer, 900 and 800, the reduction degree somehow becomes lower than 700. I think this is in line with what was found by the Dr. Ashok, where he said that if you do hydrogen, maybe there's some microstructural evolution. But if you use ammonia, ammonia may help to avoid the sintering to take place. So this is probably the same thing. There's microstructural evolution at high temperature that hinder the reduction of the oxide. And we perform experiment also using different sample mass between 100 to 500. And we found that the smallest mass giving the highest conversion, while the largest mass giving the lowest one. So this indicates that apart from diffusion within the particle, there's also intra-bed diffusion. So basically, if you introduce higher mass, you end up with thicker bed, and with thicker bed, you need to diffuse a bit harder than if you have a thinner bed. And similar to other presentation, we also try to see which model suit our data. And in this condition, we found that the diffusion, three-dimensional diffusion gender model, give the best fit across all temperature. And we try different models, but this is the one that giving us the highest R square. Also from here, we try to extract the activation energy. It's interesting that between 500 to 800, activation energy is positive, whether you perform the experiment 10 minutes, 30 minutes, 60 minutes. But once you go above 800, the longer you do the experiment, the activation energy decrease. So that's another probably indication that there's some microstructural evolution that hinder the further reduction with increasing temperature. So we also did bench scale tests using a larger mass. Before it's only 300 milligram. In this one we did 25 and 50 gram inside a fixed bed reactor. So basically this one is to simulate what happened in the reduction kiln or rotary kiln, and the product we melt it inside a vertical tube furnace. This is to simulate what happened in the electric furnace. And for the size, it's different for the TGA. We use the particle as received after crushing and grinding. So we have a very wide distribution range, and maybe it's quite similar to what we found in the industry. But for the ore, it's still the same ore. So this is how we do the fixed bed reaction. We have a quartz reactor, and then we have some filter here made of quartz, and we put the ore, and then we blow the gas from the bottom. And also we have a filter at the top to prevent any dusting. So everything that we put in stay inside. And the ore weight is between 25 to 50 grams, so quite huge. And the temperature from 500 to 900, holding time 2 hours, reductant between 25, 50 until 75% hydrogen in argon, and flow rate 5 liters per minute. Later I will explain to you why it's 5 liters per minute. And this is the reactor before the experiment. This is the ore before reduction, and then this is the calcine. So you can see it change in color. And the calcine goes to the melting stage around 1550, holding time 2 hours, condition inert. And we use MgO as a crucible. Why MgO? Because in the electric furnace, we use MgO brick. That's the mixture in the MgO, and then at the bottom is the melting sample after the melting at 1550. So this is the reason why we use 5 liters per minute. We get a help from our colleague to perform CFD. Basically, if you can, you see in terms of velocity counter, 5 liters per minute is better than 2.5. 7.5 liters per minute is even better. And from the real experiments, we can see fluidization appear very clearly in the 7.5 liters per minute. But unfortunately, we don't have a cyclone to capture the dust. So at that point, we just decide let's just do fixed bed to minimize the solid entrainment in the gas. So whatever we put in, stay there. And if there's any mass loss, it's mass loss due to reduction. So this is the highlights of the result. It's clear that with increasing temperature, the mass loss increase. But interestingly, it's not clear as before, where you have with increasing temperature that 800 and 900 decrease. Somehow in here, the trend is monotonic. It always increases. What is interesting is that the gas concentration is not, doesn't give any effect. Yeah, the effect is very negligible. So you don't have to go to a very high hydrogen concentration. 25% is sufficient. And there is the visual characteristic of the product. From ore until calcine from 900 degrees Celsius. And we try to compare the particle of the initial ore and the calcine from SEM. From SEM, we cannot see the difference. But when we did particle size analysis, it's quite clear that with increased temperature, there's an increasing trend in the size. So that somehow indicate there's some agglomeration during heating. So this is the problem maybe later in the industry. If you perform experiment at too high temperature, at one point the particle may grow, and probably it will change the dynamic of the reaction. And we also look at the XRD to track down the mineral decomposition and to track down the formation of different phases. Not only XRD, but also we do scanning electron microscope coupled with automated mineralogy and image capture system. Basically, both results are the same. Initially, let's say we have goethite, FeOOH, yeah, goethite, the brown one, and also we have talc, yeah, and also we have enstatite, which is MgSiO3, yeah. You can see the color. Most of them is brown. Initially, it was goethite with a little bit of talc and enstatite. But when we heat it up to 500, all goethite changed to magnetite, and the rest is not that significant. But when you go to 700, it's interesting that we have completely different phase. The dark blue is phaolite, which is Fe2SiO4, and also forsterite, Mg2SiO4. It means that during the reaction, it's not only reduction, but also there's interaction of the oxide with the silicate. And that's the problem, because when you do reduction, once you form phaolite, it's very hard to reduce it back to metal. Yeah, so then we melt the calcine, and this is the result of the melted calcine. This is the metal, the slag, this is the MgO crucible, and this is the olivine crystal. So from here we can see that the melting successfully separate the metal and the slag. Also the metallic phase contain mainly iron, nickel, but nickel is very dominant. Why nickel is very dominant? Because we can see that there are many iron oxides still there in the slag. So it's not that successful yet, but we try to find how to increase the reduction of this iron oxide so everything goes into the slag. Everything goes into the metal, I mean, from the iron oxide in the slag to the metal. We also try to check the slag that we have by plotting it into the pseudo-ternary diagram of iron oxide, magnesia, silica from FACSAGE. And then from FACSAGE, basically, it says that it will be somewhere in the olivine primary phase field, which is confirmed by the microstructure. And also the liquidus is 1500. And so basically it's in line between our experiment and FACSAGE. Also, our slag composition is somewhere around an industrial slag composition. So it looks like the result demonstrate that the slag that produced from here is basically the same as the one in the industry, and this is show that the practical applicability of the hydrogen reduction route for the nickel laterite processing. So how can we implement this into reality? So we talk with some of the researchers in Korea. They already start to use hydrogen in the rotary kiln at one point, but they said that it was not a good result because too many risks. There may be explosion. So maybe one of the possibility is this nickel smelting technology, where they not using rotary kiln, but they use what do you call it, fluidized bed. Yeah, but of course this process has disadvantages. It's not a common process, high capex, difficult to operate, and etc. So it's still not solved yet, but we still have to think about it. Okay, so maybe in this process we can put hydrogen as a fuel or as a reductant, and maybe electric furnace can be use electricity from a more sustainable source. Yeah. So in summary, hydrogen reduction of saprolite ore is controlled by reaction diffusion, microstructural evolution, and interaction of the product with other minerals. And we would like to thank the support by the Technology Innovation Program, funded by the Korean Minister of Trade, Industry, and Energy. And thank you. If you have questions, I welcome your question. Thank you.
Any questions from the audience? Anybody? Professor?
Dr. Taufik, very nice presentation. Thank you. Can't we go with pelletize and then hydrogen reduction instead of this fluidized bed? Because fluidized bed have already a lot of complexities, certain process. I don't think commercially some processes at high temperature fluidized bed things are available.
Yeah, I think that's a good point. Actually, at one point I discussed this with some researcher in Canada. They tried that way. Instead of using fine ore, they use like pelletize.
Yes.
And this actually already done by some researcher in Canada. I think that's an interesting way to do it, because with that one, as you mentioned, it's reduced complexity, such as less dusting, less entrainment of solid into the gas. But in the same time, we need to think about in terms of limitations such as diffusion, etc. But I think that's another aspect that we also need to study further. Yeah, thank you very much. Yeah.
Thank you.
Any more questions? Thank you.
Yeah.
Thank you so much. A big round of applause. You have a questions? Sorry, please.
Okay.
Thank you so much. Very nice and interesting presentation, Pak Taufik. My question is about, during you select the particle size, do you test again the composition of each particle?
Yep. Yeah. With the shifting, for the second experiment where we use fixed bed experiment, we ensure that all the material from the initial one pass through the shift. So if you combine them together, the composition should stay the same. But it's true, if we, let's say, grind the sample and then shift and only take the under size product, separate the bigger size product, the composition will change, because we found that some mineral is very soft. So when we grind it, it tends to go to the finer size, and some material is very hard, it stay in the larger size. So we have to avoid that one. Yeah.
Okay, thank you. So maybe for kinetic study, it is important when we study particle size, we should characterize again the composition for each particle size.
Oh,
if we study kinetic for particle size variation.
Yeah, that's true. Like, so for the TGA, we actually send it again for analysis, because we're not too sure the composition stay the same, because we only take the fine size.
Yeah.
But for the fixed bed, it will stay the same, I think.
Yes,
yeah.
Thank you.
Okay, thank you.
Dr. Taufik, you have another questions from the audience. Please come.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. Thank you for the opportunity. Thank you, Mr. Taufik, for the insightful presentation. My name is Lutfi from the Department Metallurgical Department of ITB, and I have two questions. The first one is, why are no metallic peaks observed in the XRD result at 500 and 600 degrees Celsius? And the second one is, why is nickel more dominant than iron in the smelting product of metal? And is this influenced by the partial pressure of the reducing gas? And is the formation of phyllite is affect this also?
Can you repeat the first one?
The first one is, why are no metallic peaks observed in XRD results at 500 to 600 degrees Celsius?
Yeah, okay, so why there's no metallic peak, but when we melted, we formed the metals. So that's because of, it's a very fine metal. So maybe if you can see, like, the nickel oxide in the ore is only 2%. And if you form metal at 500 and 600, it doesn't have time to agglomerate and combine together. So when we analyze with XRD, the peak will be very minimum. It's not feasible. So that's why. But at higher temperature, it has time to combine together, and XRD start to pick up the signal. Yeah. And the second one?
The second one is why is the nickel more dominant in the iron, in the metal phase, and is this influenced by the partial pressure of the reducing gas or the formation of the phthalate?
So yes, unfortunately, the slag still contain a lot of iron oxide. We believe that it's because of the formation of phthalate. As you can see in the SEM AMIX data, suddenly percentage of phthalate increased at 700 and 900. I think that stay as a phthalate, and when you melt it, it's just purely just melting. There's no further reduction, because in the melting we don't introduce any reductant. Yeah.
Thank you.
Thank you, Dr. Taufik. A big round of applause for him. It's now a privilege to introduce Dr. Arup Kumar Mondal, who is online. In fact, we are missing him from the day we started from India, and still we are missing him. But he has not, given a chance to meet his students. So he is always everywhere. Now he is online. He will be meeting all of you. He was supposed to be here, standing in front of you, speaking in front of you. And some reasons, I think Professor Julfi has explained in the morning. It's really unfortunate that he was not there physically here, but I think mentally and online he is present here outright. So to introduce Dr. Mandal, he is Associate Professor of Department of Metallurgy and Material Engineering at NIT Durgapur, which is a premier institute. And he completed his doctoral study in metallurgy at the IIT BHU, where from Dr. Raj, Professor Raj also has passed out. Prior to his appointment at NIT Durgapur in 2018, Dr. Mondal had a technical leadership position as Senior Technical Officer at IIT BHU. He possesses substantial industrial experiences in blast furnace operations and process optimizations, having worked at Tata Metallics, now Tata Steel, Sri Metallics Limited, and Kajaria Iron Casting Limited. He has published more than 50 journal papers and holds 3 granted patents. He is the recipient of IM Certificate Honor Award in 2024. Dr. Mandal has strong international collaborations, notably under India-Australia bilateral research program. He contributes to national green steel and sustainable metallurgy initiatives. He has served as principal investigator and co-PI of multiple Government of India funded projects from ANRF to the Ministry of Mines. He currently supports strategic projects aligned with the Prime Minister-led government programs of India and Australia. He has contributed extensively to the teaching and academic administration, has served as Associate Dean, Academic Undergraduate at NIT Durgapur. He has a long-standing association of Indian Institute of Metals, which has served as council member in financial year 2023. He is now Honorary Secretary of Durgapur Local Center of the Institute of Engineers. I think floor is yours, Professor Mandal.
Yes, am I audible?
You are audible, and visible also.
Okay, thank you, Dr. Majumdar. I sincerely apologize for not being able to attend the seminar physically due to some unavoidable reason. I think it is mentioned by Julfir today. However, I am grateful to the organizer and Julfir also for providing the opportunities for this online presentation. I am trying to share my screen. Yeah. Is it visible to all?
Yes, visible. Make it full. Right.
Yeah.
Good.
So, as already Dr. Mojumdar has extensively talked about me, so I will discuss about some sustainable steel refining by hydrogen plasma. From the morning, I attended some lectures. The reduction, hydrogen-based reduction of different oxides, and steel making, iron making. You have heard about it, and I will primarily discuss about the steel refining, from by the hydrogen plasma. I am from NIT Durgapur, National Institute of Technology. It is situated in eastern part of the India. Uh, where it is called Durgapur is called a steel city, because near about the Durgapur we have near about 40 to 42 numbers of industry, including MSMEs and large sectors like Steel Authority of India Limited, Durgapur. This NIT Durgapur established in 1960, and it is transformed to NIT, centrally funded institute, in 2024, and now it is uh, Ministry of Education funded Government of India organization. We have engineering, science, management, as well as humanities section. And in engineering, we have the metallurgical and materials engineering. We have research facilities, center of excellence, as well as central laboratory facilities, innovation and incubation center, and dedicated IP cell in this institute. We have a strong international collaboration, and your institute is missing here. I think in next presentation, when we will visit, our next presentation will be done by me, then your institute will be added here. So in steel production routes, if you see, it is generally the two-stage process: iron making followed by the steel making, and it may be conventionally by blast furnace as well as the electric arc furnace route. If you see, India is the second largest steel producer in the world, and we are targeting to produce 500 million ton by 2047, as per our government's target. In this presentation, I will discuss about the plasma arc melting furnace work. This is our indigenously fabricated transfer arc plasma furnace. And this transfer arc plasma furnace, we have done a lot of smelting studies for recovery of multimetallic components, for recovery of aluminium, or for production of crude steel, stainless steel grade. And in this presentation, we'll focus about the steel refining. If you see, for producing 1 ton of steel, near about 4 ton of total raw materials is required, and near about 0.8 ton of solid waste is generated. And if you see the major waste which is generated, as it is the slag one. Okay. And slag generation, it may be from the iron making area, primary steel making area, as well as the secondary steel making area. And why this slag and huge amount of slag is generated? Because steel making is process of the removal of these impurities like carbon, silicon, phosphorus, sulfur, and manganese. Carbon is removed in the form of carbon monoxide, CO2 formation. It means the product is the gaseous in nature. In case of silicon, it is produced oxidized to form the SiO2, and it goes to the slag. And also phosphorus in the form of P2O5, and sulfur to form the calcium sulfide. Then if you see, except the carbon impurities, all impurities are removed through the slag phase. Therefore, a lot of slag is produced. Okay. So due to the chemistry of chemical affinity of impurities present in the steel, it can be goes for removal. It is obviously the two-step process. One is oxidizing, another is the reducing. And therefore, always if you see overall process is a double-step process. Okay. And as all impurities are removed through the slag phase majorly, then the lot of slag is generated, and this slag having the problem of like high alkalinity, which cannot be directly used for landfilling or not used for sub-base or road materials. You have to treat it, then you can utilize. Or some basic slags you can steel making slag you can use as a substitute of the limestone charging inside the blast furnace, or some amount as a sinter mixed material. So if you want to produce the steel in a sustainable matter, obviously the all impurities your target will be, it should be removed in a single stage, or you have to minimize the slag generation, or less or least zero slag generation. As this impurities removal is done in case of BOF, if you see this, it is oxygen is injected, then you have to inject some other gases in place of oxygen, because oxygen, as I have discussed, it cannot reduce remove the sulfur. Okay, therefore we go for the double step. Then in place of oxygen, if we introduce any reactive gases which can directly react with all impurities present. So hydrogen is a gas which can react with all impurities present in the steel or liquid iron, like carbon, silicon, phosphorus, sulfur, manganese. But if you see the thermodynamically possibilities of desulfurization is actually, if the hydrogen is in the form of gas, then from the gives free energy. The desulfurization of molten iron with molecular hydrogen is impossible or difficult. And if you go for the plasma, then obviously it can produce react with the steel sulfur to remove the sulfur, and which requires more than 2500 degrees centigrade temperature. And this high temperature, it can be generated only by this plasma. It is also supported by this fact stage study. Then near about 2700 Kelvin, it means more than 2500 degrees centigrade temperature is required. In case of transferred plasma is having some benefit, like high temperature generation as compared to the non-transfer. And another benefit is, like if you see in the normal electric arc furnace, this is the transfer type of furnace, transfer arc type of furnace. And if we go for modification of this plasma unit to from the existing unit of electric arc furnace, it is possible very effectively. Therefore, in existing system, we can adopt this transferred arc plasma system efficiently as compared to the non-transferred. For these studies, we have taken typical pig iron, which contains a high amount of gangue content. You can see here near about 3% carbon, 4% silicon, high amount of manganese, phosphorus, and also sulfur. Actually, this typically blast furnace pig iron. It is generated when you do this lining, or you start up the blast furnace. Therefore, the heart temperature of this furnace at that time it decreases. It is lower, and high carbon consumption is there. And therefore, you will get some typical type of pig iron there. We have collected this type of pig iron for this specific study. And for making different sources, we different composition of this melt, we have also use MS rod as well as the hoop iron, which is almost a pure iron. If you can see the chemical composition of these raw materials. And for this plasma source, we have used hydrogen as well as the argon gas. And we have prepared different system like APS system, AP, MNS system, APS, SI system, APCS system to see the different effect of the impurities for the sulfur removal. And this is our setup for doing the experiment. Then we have taken 4 kg pig iron, and we have done different heats having different composition of argon and hydrogen plasma. And we have done after melting in the normal arc, we introduce the hydrogen plasma or hydrogen argon combination plasma. And after a regular interval, we have taken the sample and we analyze how much impurities is present. And different parameters here mentioned we have maintained for this study. And this is the removal trends of carbon, silicon, manganese, phosphorus as well as the sulfur. If you see, the carbon removal is very faster, followed by, if you see, the sulfur, silicon, and removal of this manganese and phosphorus is slightly lower at a longer exposure time, then the removal is high. But if you see, the drastic decrease in carbon or removal of carbon is happened. This carbon is actually interstitial position carbon is present. When the hydrogen plasma is injected, it is reacted with carbon very faster way and it removed very easily. Then we have determined the degree of removal, and if you see, the removal, as I discussed, when sulfur hydrogen will react with the impurities, it will form the gaseous substance. So gaseous substance, we have collected the gas composition as well as the collected the vapor as well as the dust from the exit gas. These are the composition. Then a very trace amount of sulfur was detected in the gas analysis. Then we have done this CSCAD modeling to understand the sulfur behavior during hydrogen assisted refining process. If you see in the first figure, hydrogen is introduced into the electric arc furnace environment along with crude steel system. Then this model tracks the material balance and chemical transformation occurs inside the furnace at high temperature condition. The simulation predicts an overall crude steel production approximately 4,000 units, where the hydrogen continuously injected in the refining zone. Then the second figure, it is focused on the sulfur distribution after the hydrogen addition. From the sulfur mass balance, you can observe only about 0.4 units of the sulfur remain in the crude steel, whereas around 7.6 units are transformed to the exit gas. This clearly indicates that the sulfur is preferentially removed from the molten metal phase. The third figure, if you see, it explains the mechanism behind the sulfur removal at elevated high temperature. The hydrogen reacts with the dissolved sulfur present in the molten steel and slag system to form the gaseous sulfide or H2S. Therefore, this hydrogen actually reacts with the sulfur to form the hydrogen sulfide gas. Finally, from this study, we can say that impurities removal like carbon, manganese, silicon, phosphorus, and sulfur from the pig iron metal by hydrogen gas under transfer dark plasma furnace with which we have done up to 70 minutes of plasma exposure. It is possible, and all impurities concentration is decreased with the exposing the hydrogen plasma, reaction time increasing. And if you see increasing the flow rate of hydrogen, like 0.5 liter per minute to 2 liter per minute, the impurities removal is increases. And if we um, see the changing in the composition of the argon as well as the hydrogen, what will happen if you decrease the argon content? The hydrogen arc instability we have observed. Therefore, argon is as a stabilizer gas, argon is required. And the gas mixture like 1 liter per minute hydrogen and 1 liter per minute argon gas, it gives the maximum impurities removal. Even greater than 2 liter per minute means increasing the hydrogen level. If we increase also, then also the removal it will decrease. This is not this is actually for the instability of the arc, because stabilizer gas, if we decrease it, the maximum impurities removal we achieved up to the 70 minutes of exposure time. It is near about 99% of total carbon present in the liquid metal, it will be removed, and near about 81% of sulfur, 76% of silicon, 41% manganese, and 31% of phosphorus. The major reason for manganese and phosphorus, lower removal of manganese phosphorus, is actually the this system is actually our system is not airtight system. During taking all time sample for the kinetic study, always air entrapment, it provides a thin layer of the slag layer formation. Like in FeSMN system or FeSP phosphorus system also, if we observe, then the thin layer of P2O5 and MnO oxides layer is formed, which actually restrict the further removal or further reaction of hydrogen with the metal layer, because it acts as the barrier. Therefore, these two elements removal rate is lower. Thank you. If you have any question.
Thank you, Professor Mondal. Any questions for Professor Mondal? Yes. Okay, let him.
Yes, my name is Shawadiullah, and
yeah.
Thank you, Srinath. I am a doctoral degree student here in ITB, Indonesia. Sir, I have one question. You mentioned that in your presentation that you are doing the process of dephosphorization and desulfurization. What do you think what will be the outcome and why it is necessary in your research?
Actually, I have discussed the aim of this work is the steel production, steel making. Steel making means from the pig iron to produce the steel. Okay, so steel making is it means the impurities removal. Impurities present in the liquid metal, you have to remove it. So impurities present in the form of carbon, sulfur, silicon, phosphorus, etc. And the conventional steel making process, if you see, it is you cannot remove all the impurities in a single step, because you have to create the oxidizing atmosphere first, so that the impurities like SiO2, silicon, phosphorus, manganese, carbon, both these impurities will be removed. After that, you have to create the reducing atmosphere so that you can remove the sulfur one. But hydrogen is a gas. If you introduce in place of, like in basic oxygen furnace, we introduce oxygen, okay, for removal of impurities. If we introduce hydrogen, what will be the effect? This is our main objective of the study. Then this hydrogen as a reactive one, it can react all impurities present in the liquid metal, okay. But hydrogen having difficulties in this way, like normal hydrogen, you cannot, it cannot reduce. If we go for ionized hydrogen or plasma hydrogen state, then only it can react with the sulfur, and temperature requirement is near about 2500, then you can remove it. Therefore, this is the phosphorus removal or sulfur removal aim is to remove these impurities for making the steel.
Thank you, sir. Thank you, sir.
It is clear?
Yeah, it's clear. Actually, sir, we are also using almost the same element from these functional groups. So
Yeah.
I was want to know about that very clear. Yeah, thank you so much, sir.
Okay. The removal of, for your information, actually this plasma, for removal of these refractory metals also, you can remove from this liquid, means for purification of this any liquid metal, like high temperature materials, molybdenum type of impurities, if it is present, you can also remove by this hydrogen plasma.
Professor Arup,
yes, sir.
I am Zulfiari. So your suggestion is to make this kind of symposium. Is correct?
Yeah.
Yeah, we have
Actually, I initiated this one, and I missed.
Okay. So thank you for a very impressive talk about the hydrogen plasma for refining of the steel. So my question is, we know that the mechanism for sulfur removal due to the formation of H2S and also silicon can be removed easily due to maybe the lowest melting point of silicon, etc. And could you explain actually what is the mechanism for carbon removal by hydrogen plasma? What is the mechanism? Because there is no oxygen, and how carbon can be removed?
Initially, the methane will form. If we generate the control atmosphere, then obviously the exit gas, it will contain CH4. In our exit gas also, some CH4 we have got. But what happened? When we want to collect the sample periodical manner, then we need to break this seal. Okay, always. In our system, existing system, so always air entrapment creates the conversion of this methane to finally it is CaCO2. Some amount of CH4 we have also detected in our exit gas. Otherwise, if you create the control atmosphere, this chamber is, if it is airtight or controlled atmosphere you can generate, then obviously the CH4 will be there.
Okay, in terms of economical aspect, so now we use oxygen for refining. What do you think if you compare oxygen and with hydrogen plasma for removing all the impurities?
Yes.
Okay, thank you.
It will be costlier. In present condition, obviously it will be costlier. So similar thing I faced yesterday's meeting with ministry, that how it will be economical in nature.
Thank you, Professor Mandal. It was nice
you.
hearing from you. And we are still missing you. And
Yes.
a big round of applause for Professor Mandal, please.
Yes, in future I will again visit if Zulfir invite me.
Yes, later on you can come down. Yes, no problem. So I
Okay,
think with this we come to an end of the plenary session 2. And this session was full of, a lot of informations. Started with Professor Raj Dishwar, then Madam from Swinburne University, then Professor, I correct myself, Dr. Taufik, and then Professor Arup Mandal. It was nice hearing from all experts from plasma and hydrogen industry. Thank you so much. It was really a privilege for me standing and conducting this session. Thank you one and all.
Okay, thank you to our moderator, Dr. Argia, for facilitating this insightful session. Please give applause for Dr. Argia. Ladies and gentlemen, we will now proceed to our next agenda, the coffee break. Coffee break refreshments are available in right side of the main entrance. Kindly proceed to the designated area. Please enjoy the refreshment and take this opportunity to network and engage in further discussion with fellow participants. Please note that we have approximately 20 minutes for this break. The symposium will continue with plenary session 3 at 2:65 p.m. GMT +7. And please enjoy your refreshment. Ladies and gentlemen, plenary session 3 will begin in 5 minutes. We kindly request everyone to make your way back into the hall and take your seats. Thank you for your attention. Ladies and gentlemen, the plenary session 3 will begin. We kindly request everyone to make your way back into the hall and take your seat. Thank you for your attention. Okay, Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, to keep spirit for ourselves throughout this session, please give applause for us. Okay, now we will go to plenary session 3. To guide the session, we invite our moderator, Mr. Fahreza Abdul PhD, to come to the stage. To Mr. Fahreza, the session is yours.
Good afternoon, everyone. Okay, thank you so much for the opportunity from MC. Now, Faris Abdul will guide the session. We move to parallel session 3, and in this session, we still have 3 distinguished speakers. These come from Swinburne University of Technology, Australia, and then from Institute Teknologi Bandung, and then from Kazi Nazrul University. And for the first speaker for this session will be Mas Made Girinata from Swinburne University of Technology. Hello, Mas Made, can you hear my voice?
Yeah, thank you, Mr. Fariza, Dr. Fariza, for the welcome.
Before presentation, you have 20 minutes for presentation and followed by discussion for 5 minutes. Time is yours.
I will share the screen.
And I'm sorry, I also want to introduce you. Mas Made is doctoral student, right now?
Yeah.
Yeah, doctoral student at Swinburne University of Technology, and he also earned his Master of Science and also undergraduate create from the Metallurgy Engineering, ITB, and the project and professional experience. He now Associate Research Fellow at University of Wollongong, Australia, and he also has some publication and conference related to extractive metallurgy. Okay, time is yours, Mas Made.
Sorry. Thanks for the welcome. Good afternoon, everyone. Once again, my name is Made Girinata, PhD candidate from the Swinburne University of Technology. Today, I will present my work about hydrogen reduction of AIF dust and its key constituents. This work is co-supervised by Professor Akbar Ramdhani, Professor Jeffrey Brooks, Professor Brian Monahan, and Israel Mugras from Wayala Steelworks. This work is supported and funded by Australian Research Council, Steel Research Hub, Fund Steel Wayala Steelworks, and Swinburne University of Technology. So, to start this presentation, I would like to talk about iron and steel making process pathway. So generally, there are 4 ways to produce steel. First, via a blast furnace BR process, which is
sorry,
the most
Mas
common.
Made, for interruption.
Yeah.
Can you make your screen full?
Oh, this is already full in my laptop.
Maybe yes.
Oh, sorry, it is not. Wait, sorry, how to do that? Option, screen. Okay, I will stop share first, probably.
Okay.
Share setting, share, enter into full screen. Wait, is it changing now?
Okay, nice.
Okay. Sorry, once again, to start this presentation, I would like to introduce a little bit about iron and steel making process, by the way. So there is four way to extract or produce steel. First, the common one via blast furnace and BOF process, which is accounting around 70% of the total steel produced. And then this, wait, sorry. Okay. And then the second one is direct reduction process, which is accounting around 8% of the total steel produced. And then the last one is via scrap recycling in AIF remelting process. So overall, steel industry is one of the biggest industry in the world. We currently produce around 1,600 million tons of steel globally, and then in the future, it's forecasted to be 2,500 million tons steel globally. At the same time, this industry also producing quite a number of carbon emission, roughly around 1 tons carbon emission produced per ton steel. So in the future, we need to decrease that by 90%. There is two ways, at least, to decrease this emission is by using secondary resource, which is scrap and other byproducts that contain iron, and also try to replace current energy resource to renewable energy and reductor to biocarbon or hydrogen. In this case, I will focus more into AIF process. So roughly we need around 1,100 kg to produce 1 ton of steel. But at the same time, it also produces byproduct, roughly around 50 to 20 kg. This byproduct called AIF dust. As the scrap utilization increase in the future, the AIF dust production is also increasing. As I mentioned before, AIF dust is one of the byproducts that contain a high amount of iron and zinc, mainly present as magnetite, zinc oxide, and zinc ferrite. Conventionally, to utilize this AIF dust, we use a waste kiln. Basically, it uses carbon and focusing to recover zinc. But in this case, the iron in AIF dust will be wasted, and this process also producing quite big number of carbon monoxide. So in the study, we try to mimic the hydrogen direct reduction iron making to lowering the carbon emission and increase the plant sustainability. Sorry. So this presentation will basically talking about hydrogen reduction on AIF dust and its key constituents, which is zinc oxide and zinc ferrite. We focus on the mechanism of the hydrogen reduction using the microstructure evolution and then composition analysis. So to do the experiment, we use electric horizontal furnace. They're equipped with magnetic stick sample holder. At the same time, on the other side, we also equipped with the condenser to catch the gaseous product, such as zinc and other valuable metals later on. Before we analyze the product after the reduction, we also check the pellet before the reduction. This pellet is basically a dense pellet, especially for zinc oxide and zinc ferrite. On the other hand, for AIF dust, because AF dust itself is a complex minerals that contain a lot of other impurities as well. So it's a mix between a lot of material in different size as well into the pellet. So after this, we try to look at the difference and how the microstructure evolution is, and then we also analyze the overall mechanism based on it. And here is the cross-section of the zinc oxide pellet at 800 degrees Celsius using 15% hydrogen and argon gas mixtures. As we can see here at the center and the surface of the pellet, pores is formed uniformly. And at longer temperature, the pores grow. At the same time, based on the macro observation, the pellet size is changing, and then it's become the size becomes smaller due to zinc gasification after the reduction. Because of the pores formed directly after the reduction uniformly, we based on our analysis, the overall reduction not affecting by the diffusion of hydrogen, which means it's more affecting by the chemical reaction, and the the increase of temperature directly increase the overall reduction rate. More detailed study is found in this paper about zinc oxide kinetics and microstructure analysis. On the other hand, at zinc ferrite, the presence of iron will affecting the overall reduction due to the product layer formation. Based on the microstructure analysis, there are 3 different product layers that form. The first one here is at the product layer that form at low temperature that the zinc oxide is not yet being reduced or still limitedly reduced, and because of that, the product layer is basically semi-dense, but at the same time, iron is reduced, which means the reduction happened due to diffusion of the hydrogen underneath the surface. At higher temperature, more than 700 degrees, a porous F iron and worsted product layer form. At deeper part, there is an intermediate base layer where the diffusion and the reaction mainly happen. And after that, at the core, there is an unreduced layer. At certain temperature, where the sintering rate is higher compared to the reduction rate, a dense product layer is formed, which means this layer could block or hinder the penetration of hydrogen and change the overall reduction mechanism from diffusion of the gas to diffusion of the gas through the solid dense layer. Here is the summary of the microstructural evolution of the zinc oxide pellet product layer. So as we can see here, at lower and early reduction time, semi-dense or fine porous zinc oxide content product layer is formed, and then at a higher temperature and longer time, a porous iron or worsted product layer form, and then later, when the sintering rate is higher compared to the reduction rate, a dense product layer is formed. Here is the comparison between zinc oxide reduction mechanism. Basically, at zinc oxide reduction, the reduction happen uniformly, and the overall mechanism is depend on the reaction between hydrogen and zinc oxide, which is more likely influenced by the temperature. Meanwhile, at iron containing kin constituents such as zinc, ferrite, and magnetite, the product layer form. And this product layer will changing the dynamics of the mechanism due to the blocking of or the blocking of the hydrogen penetration into the unreduced part of the pellet. Now, at the AF dust itself, it's more complex compared to pure minerals like zinc ferrite and zinc oxide. So we use AF dust from one of the steel works in Australia. This AIF dust, as we can see in ICP, IIS composition analysis, and XRD analysis, is contain mainly iron, zinc, and calcium oxide. Zinc mainly form as zincite and zinc ferrite, meanwhile iron form as hematite, ferrite solid solution such as magnetite, and form a solid solution with zinc, magnesium, and manganese. Meanwhile, calcium from fluxing material will form as calcium oxide and calcium carbonate. From the optical microscope and SEM image, we can see there is quite different particle size and shape. There is a globular shape particles. There is irregular shape large particle, and also globular but nano metal sized particle. Nano sized particle more likely form due to vaporization during melting. Meanwhile, the large globular and irregular particle coming from the rejection of the liquid metal or the slag, or solid rejection from the input. Not working. Sorry. So here at 600 degrees Celsius, at 2 hours reduction time, we can see here that the overall microstructure not changing much. Is still similar to the raw materials. Based on the XRD analysis, the iron form, meanwhile zinc oxide is still there, which means the reduction of zinc oxide is still limited. At higher temperature, at 100 degrees Celsius, two different zones form. At the right side, darker zone, which is the reduced part, and then the left side is the unreduced part. Based on the XRD analysis, more iron form and lower peak of zinc oxide form. And at 1000 degrees Celsius, most of zinc oxide is reduced and removed. Meanwhile, iron peak is increasing. At the same time, the impurities, mainly calcium based oxide, is also around the reduced iron. When we see here at the reduced zone, the fine particle will form as a fine Fe metal and a calcium-rich oxide. Meanwhile, the large Fe particle is also reduced and then still form as large metals. When we see the EDS mapping analysis, on the dark side, there is no zinc, which means all the zinc is reduced, and then the iron iron color is more light, which means iron is also formed as metal. In this case, it's similar to zinc ferrite, which means the reduction happened from the surface to the core, and basically it's affecting by the diffusion of the hydrogen. And we also, analyze the condensed product. Basically, we could separate the zinc in front of zinc metal and zinc oxide. And at the same time, we also could recover some valuable minor metals, which is bismuth as bismuth oxide, and then lead as lead metal, and cadmium as cadmium metals. And also, we could separate the impurities, which is salt, alkali salts, such as sodium chloride and potassium chloride. So the conclusion is, first, zinc oxide reduction occur uniformly, form as zinc gas, creating uniform pores in the pellet. And then zinc ferrite, on the other hand, three zones form observed. The first one, the unreduced core, the intermediate phase layer, and the product layer. These three zones form due to the diffusion of the hydrogen from the surface to the core. And then at different temperature, three different product layer microstructure is formed. First, at lower temperature, zinc content product layer form, and then at higher temperature, porous product layer form. And at higher sintering rate, iron dense product layer is formed. AF dust reduction follow like zinc ferrite mechanism controlled by diffusion. The reduction occurred from the surface toward the core. The product layer hindered further reduction, while the removal of zinc oxide helped to promote pore formation. And solid-state hydrogen reduction could efficiently separate valuable metal, producing a very rich pellet and a condensed gaseous product contain zinc, bismuth, and lead. Thank you, everyone.
Okay, thank you so much. Give applause to Mas Madegiri. And now is the Q&A. Maybe from the audience, do you have question regarding the Mas Made presentation? Okay, I will start from me, I think. Mas Made, can you hear my voice?
Yeah.
Okay. From zinc ferrite reduction, how you define each zone? You say you have three zones, reduced zone, then intermediate, and unreduced zone. How define it? Only based on morphology, or you do another evaluation?
So thank you for the question. So basically, we analyze based on the composition as well as the morphology. So on the composition, we could say at the unreduced zone or the core, there is not much composition change. Meanwhile, at the intermediate phase, there is a slope where there is a reduction of oxygen composition in there, while the iron is also increasing. And then at the product layer, it's only basically iron. So which means the reduction is finished in the surface layer.
Okay, thank you. So you combine morphological evaluation and also compositional evaluation like that? Okay.
Yeah.
Maybe from the audience, do you have question? Okay. Okay, I think enough. Thank you so much, Mas Madegiri Nata. Thank you so much. We can move to the next speaker. The next speaker will be from ITB, Mbak Shani Sofia Faud. Mbak Shani, please. Okay, I will introduce you to the audience. Mbak Shani now is a master student, PhD student, master student? Yes. Okay, master student at Pyrometallurgy Laboratory Research, ITB, since 2024 until now. And she got the undergraduate degree from Universitas Hasanuddin, Makassar, South Sulawesi. And today, Mbak Shani will present about her research about cerium oxide reduction using hydrogen plasma smelting. And the time is 20 minutes and followed by discussion. Okay, floor is yours.
Okay, good afternoon, distinguished all the invited speaker, all the researcher, and the participant that thank you for taking the time to attend this symposium. Hi, my name is Sani Sofia Faut from the Metallurgical Engineering Research Group at the Pyrometallurgy Laboratory, Institut Teknologi Bandung, under supervision of Prof. Zulfiadi Zulhan. So, I'm a master student right now. Today, I will present my research entitled Cerium Oxide Reduction using Hydrogen Plasma Smelting. Basically, this research focused on the potential use of hydrogen plasma as a rapid reduction method for the cerium oxide toward a cerium metal. So, before we discussing about how we reduce the cerium oxide toward metallic cerium using the hydrogen plasma smelting, first I would like to start with the global background, why this research is important to do right now. So you can see on this slide, show the global energy related carbon emission. You can see on the left side is a graphic that show annual CO2 emission that increase every year. We can see in the 1960, the annual CO2 emission is around under 20 gigaton, but when in 2025, which is last year, the total CO2 emission is increased more than 40 gigaton CO2 emission. And on the right side, the graph show the greenhouse gas emission by sector, like power industry, industrial combustion, and process building, transport, fuel exploitation, agriculture, and waste. That several industry sector, including metallurgy, contribute significantly to the global emission right now. For the example, you can see above the right side of the slide, the steel production is the one of the most largest industrial source of CO2 emission right now, reaching around 4.1 billion tons of CO2 emission in 2024 and accounting for about 7 to 8% global anthropogenic greenhouse gas emission. Also, aluminum production is also contribute to direct industrial CO2 emission. You can see on the above, nearly 270 million ton direct CO2 in 2022, about 3% of the world direct industrial CO2 emission. But in metallurgical industry, not only just to aluminum and steel production that conducted CO2 emission, but also from using carbon as a reductant, electrode consumption, decomposition of carbon flux that used in a metal process, metallurgical process. So, this is why we need to do decarbonizing metallurgy is most important thing we should do right now. Metallurgical process essential for modern metallurgy, but many of them still require high temperature, fossil fuels, and a long processing route. So, developing cleaner and faster reduction method is an important step forward for us to do to low carbon metal production. Okay, to better understand why this issue is important, next slide I will show you how CO2 emission is related to carbon cycle and climate change. So, in this slide is relation between carbon dioxide in the carbon cycle and climate change. Carbon dioxide is naturally part of the carbon cycle. It moves between atmosphere, ocean, soil, plant, and human activities. However, human activities, especially fossil fuels, combustion and industrial process increase the amount of CO2 released in the atmosphere. But not all of the CO2 emission that released in the atmosphere can be absorbed by the soil and the land. So the remaining CO2 that stays in the atmosphere is the CO2 that can be absorbed in the ocean and the land. This is a video on the left side. Okay, in this video you can see the increase of concentration CO2 in the atmosphere every single month that still increase until now. And on the right side video that shows meanwhile, the video on the right side is a consequence of this increase, which is the rise of Earth's surface temperature. After understanding the global emission problem, I will now focus on the role of metallurgy, especially the production of cerium metal. So, I will now introduce what I'm doing in this research. So, in this research, I'm using, I'm learning about cerium oxide. Cerium is the one of the 70 rare earth elements in the periodic table you can see on the right side. Cerium is located in Lantanid series. Although it's called a rare earth element, but not cerium is not a rare one. So you can see at the left side it is an average crystal abundance of selected metal or element. You can see cerium is the tree with the biggest abundance in the earth with 66.5 ppm. And on the right side, the graph showed that the global rare earth mine production from 2012 to 2024, the production trend it continues increase mainly because the rare earth elements are increasingly needed for advanced technology right now. So on the right side graphic, you can see now the mine production in the world is mostly by China. This shown that cerium is not only scientifically interesting but also industrial important. Next slide. This slide I will show you some application and market example of the cerium-based material. So as you can see, from cerium oxide, this is cerium oxide I use in this experiment. So I use cerium oxide from Sigma Aldrich, which is a powder and have a 99.9% trace metal basis. So on the right side, you also can see the cerium oxide is commonly used as the catalyst, environmental application, biomedical application, coating, electronic, and polishing material. In that figure, you can see there's a lot. will allow you can use cerium in the application of catalyst and energy, aerospace and defense, coating and material science, environmental application, electronics, optics, and biomedical application. It also can be used as a polishing agent, ceramic additive, corrosion resistance, gas sensor, also a lot, hydrogen production, air pollution control, and radio protection. So, on this slide, I also show you the commercial cerium oxide, cerium metal, and magnesium cerium alloy. The price is very depending of the purity, form, supplier, and order quantity. In this market information, you can see on the right side that's cerium metal, and on the left side is a high quality rare earth magnesium cerium alloy that basically use to high thermal conductivity, because magnesium cerium master alloy can transfer heat from electronic component. It also can be used because lightweight design. The lightweight nature of this alloy can be the good thing to we use because of the lightweight design of the magnesium cerium alloy. It also customizable form factor. Magnesium cerium master alloy can be tailored to specific form factor, making them adaptable for various electronic devices. Okay, this slide show a lot of cerium-based alloy. I want to show you that cerium has a lot of application in industry. In this slide, you can see there's a lot of mineral can be combined with cerium. Cerium copper alloy particles CeCu are used as a master alloy and added to copper alloy furnace liquid. Also, a lanthanum cerium alloy is mainly used in battery production. Cerium iron master alloy used in the fire starting tools, production of rare earth steel, sticker of gas welding and cutting torch, deoxidation in metallurgy, emergency combustion device in survival kits too. Cerium also can be combined with nickel. Nickel cerium master alloy can be used as solid oxide fuel cell. Also, a catalyst converter and oxidation resistant coating for jet engine blades. Cerium also can be combined with aluminum in use in aerospace industry. Aluminum alloys are widely used at the aerospace industry due to their lightweight nature and high strength. Also used in automotive industry, engineering and manufacturing, and heat resistant application. So, this is a slide. I want to show you that compare from the conventional routes from cerium metal production and the routes that I use in the experiment. So, for the conventional routes for cerium metal production, we can use various routes. In this slide, I'll show you first route is a conversion of oxide to fluoride, and after that doing a calcium reduction, vacuum distillation, and the other route is conversion of oxide to chloride. After that doing the molten salt electrolysis, and the third route is direct metallothermic reduction of CeO2 using a metallothermic reduction using magnesium powder. From this slide, the total of processing in the conventional route for cerium metal production, as you can see, is 2 to 3 hours, 2 for 4 hours, and 4 to 6 hours. Meanwhile, the metallothermic reduction is only need 3 hours, but in my research, we doing the reduction of cerium oxide to cerium metal using hydrogen plasma smelting reactor that we have in our laboratory. And in this research, we do 2 to 8 minutes. Okay, this slide show the hydrogen plasma smelting reactor at the Pyrometallurgy Laboratory Institute Technology Bandung. You can see on this slide, the reactor used 2 gases, argon and hydrogen. Argon is used to support the plasma atmosphere inside the reactor, while the hydrogen acts as a reducing gas. Also, the system consists of a reactor chamber, a cooling system, and a off-gas system. As you can see, the cooling system is used to control the temperature of the equipment, while the reduction is while the off-gas system helps to control the gas inside the reactor and reduce safety risks. So, in this research, the cerium oxide sample is placed inside the reactor. You can see on the right side, that's where the cerium sample is placed inside the reactor. For the photograph on the left, show that operator during the experiment. Yeah, that was me. In this study, the operation was carried out manually. This means that the sample preparation, reactor operation, and plasma treatment were controlled directly by the operator. Okay, after I introduce the reactor setup, the next slide I will show you actual cerium oxide reduction process. Okay, in this slide, show the experiment process of cerium oxide reduction using hydrogen plasma smelting reactor that we had in ITB. This on the left side is the cerium oxide powder that we use. Before reduction, the sample was white. After the reduction, the sample was changed. Okay, next. Okay. Now I will show how the experimental we doing in this research. So in this research, I investigate the effect of reduction time on cerium oxide reduction using hydrogen plasma smelting. The reduction time we use in the experiment is 2 minutes, 4 minutes, 6 minutes, and 8 minutes. In this slide, I'll show you the result after only 2 minutes of the reduction under hydrogen plasma condition. We can see this is before reduction, after reduction, and the sample after reduction. We can see the initial condition of the sample before reduction is still white, and after reduction is changed, like I said before. On the above of the right side, we can see a SAM EDS result that cerium content reached 92.11 weighty% after only 2 minutes. However, the ADS mapping, you can see oxygen still widely distributed on the surface of the sample. The remaining oxygen signal may come from unreduced oxide phase or surface reoxidation after the experiment. Therefore, further reduction time is needed to improve the oxygen removal after 2 minutes. So, because of that result before in the reduction 2 minutes, we did more time to doing a reduction cerium oxide under hydrogen plasma smelting. In this slide, we do a reduction for 4 minutes. You can see this is before, after, like the previous slide. Based on EDS result, you can see on the right side, the cerium content is increased to 92.93% and the oxygen is 7.07. Also from the EDS mapping, the oxygen still observed on the surface of the sample, but if we compare to the before the 2-minute sample, it
sorry,
less.
Sunny, can you move faster because time is up here.
Oh yeah, this is before the 2 minute and the 4 minute. You can see the difference. After that, this is 6 minutes of reduction cerium oxide to cerium metal using hydrogen plasma. You can see before, after, and the sample. We can see the SAM EDS result is increased again to 94.92 WEC-T% and the oxygen is 5.08. We can see also the mapping here. There's some part of nothing oxygen content there. We can see at the picture. Yeah, this the different 4 minutes and also 6 minutes. Next, this the sample after 8-minute reduction. We can see before, after, and the SAM EDS result. We can we can see at the result there, the cerium content is 97.04 WEC-T%, then and the oxygen is only under 3%, is 2.96. Also, the EDS mapping result, you can see there's nothing more oxygen like another minute, another time of reduction. You can see the difference is quite interesting. The oxygen is nothing much left in the sample. So, after doing that for variation reducing time is 2 minutes, 4 minutes, 6 minutes, and 8 minutes. These slides show the graph. That blue line is represent the cerium content as the reduction time increase, and the cerium content is reduced. Sample is also increased. We can see out the blue line. The cerium content is increased as more in 2 minutes, 4 minutes, 6 minutes, and 8 minutes is always increased. Also, the oxygen on the orange line in 2 minutes, 4 minutes, 6 minutes, and 8 minutes is decreased. Also, on the right side, the same result I also prepared in the form of bar chart. From this chart, we can clearly see that cerium becomes more dominant, while the oxygen becomes much lower. You can see on the right side, after a longer reduction time in 2, 4, 6, and 8. Also, in the red line, that show the oxygen removal percentage. The oxygen removal percentage also increase with increasing the reduction time. You can see reaching the highest value at 8 minutes with approximately 84% oxygen removal. Overall, these results show that the reduction time plays an important role of improving the reduction of cerium oxide under hydrogen plasma condition. So after that experiment, the summary I will say is the sample reached CE content of 92.11, 80% after only 2 minutes of processing and 97.04% after 8 minutes reduction. Also, increasing the reduction time improve the reduction behavior. Hydrogen plasma smelting reduction achieved approximately 85 oxygen removal from cerium oxide within only 8 minutes. Also, the cerium oxide reduction using hydrogen plasma smelting has the potential to simplify the overall process by reducing several stages required in the conventional method. Maybe that's also.
Okay, thank you so much. Give big applause to Mbak Shani. Yeah, thank you for the nice presentation. Next is Q&A. Maybe only one question for this speaker. Do you have any question? Okay, Dr. Ashok, please.
The 0 minute, you are showing 89% cerium.
Yes.
In your graph.
Graph?
The second last slide, 0 minute, the cerium content is showing us 89%. 81%. The pure cerium oxide should contain almost 50% oxygen.
Back to that slide.
Yes. Yes, the 0 minute treatment, there is no plasma done, but 81% cerium, how did you get? A pure cerium oxide should have 50% oxygen, 50% cerium. Roughly.
At the zero time?
At the 0. Maybe you can check the data. Yeah.
Actually, for the data I use on the 0 time, I use a manual.
How come? Based on
The data is, I'm not do the same EDS analysis on the cerium oxide sample before the reduction, but I use this data because
Okay, anyway, it's a small thing, you can check. I will also check.
Okay, thank you. Maybe that's crucial to check, Mbak Shani. Maybe finish for this session. Thank you so much and give her a big applause again. And next, we will move to the third speakers for this session, and the last speaker should be the most significant speaker in this symposium. Please, Dr. Arya. Dr. Arya is the director, School of Mines and Metallurgy, Kazi Nazrul University, and he will present his research about the decarbonized blueprint, a strategic roadmap for green steel technology. Dr. Arya is distinguished metallurgical engineer, a recognized expert in extractive metallurgy. For the education, he got all of the degree from Jadavpur University, and Dr. Arya also has published extensively in leading peer-reviewed journals and paper, and he also dedicated educator and mentor, and also has guided over 200 students across undergraduate, postgraduate, and also doctoral level. And Dr. Arya is also certified lead auditor and internal auditor for integrated management system. Okay, the time for your presentation is 20 minutes, followed by discussion. Time and floor is yours.
Thank you one and all. In fact, the seminar started with Z, Zulfi and Zulfi, and ended with Argya, A and A. So Z and 2A. It is A to Z. The seminar is totally, covering A to Z, everything. So thanks to the organizer and the symposium and the whole team of the students of Institute of Bandung, Technology Institute of Bandung, and I really appreciate the effort put by the professors and the students. Thank you one and all. So before I start, this is something which I am going to talk. I think morning onwards we were hearing so many technical issues. Students of Gen Z, we talk about some faster things, you talk about some good music, some kind of play, and not these. I don't find somebody is very much interested talking with the students that they are going into higher studies. Is it so? Yes or no? So, it's better to understand if we don't work, what is going to happen, right? So, if you see, my talk is something which is, I'm talking about 7% of the global CO2 generation, which is the most, carbon intensive industry, which is steel industry. I'm talking about decarbonization of the steel industry, a strategic roadmap. How to do decarbonization of the steel industry. Okay. Now, to understand where we are exactly, standing or rather sitting here, you see all of us, the weather is so good outside and it's raining, still somebody, without AC we can't stay. And maybe 30 years back down the line, we did not have fans, we did not have anything. And we were having good times, The temperature is really going high, isn't it? Just before my lecture, somebody was talking about carbon dioxide is growing very, very high. It's reaching very, very high in that, and the temperature is really high. And in these talk started in the year 1993, where the 1995 Kyoto Protocol in Japan, they started thinking about the industry and the steel industry, and also the temperature is going high. And now there is a target in 2015 Paris Convention, when they decided that the temperature should not cross 1.5 degree per year. So if it grows high, just we will reach 70 degree in some more times, maybe in the year of 2050. So everybody, whoever is there, sitting here outside, a human being has to work on this, right? So this is what is carbon perspective, which I'm going to talk, is that you see the steel, it is the most used material in construction and in transportation and also manufacturing. Now, if you see the global production of steel, it is around 1.8 billion ton per year in the whole world, and this is contributing 7% of the global CO2 emission. And this is, you see, steel is the bedrock of modern civilizations and one of the greatest climate challenges. Now, this is what is carbon benchmark. If you see that for producing 1 ton of steel, you are producing 2.3 tons of CO2, which is conventional steel making, BF, BOF route. Now, in case of electric arc furnace, it comes down to 1.4, 1.5, and the target is 0. So please do understand where we are shifting, and where we have to reach. So this is what is our goal. Now, if you see the climate perspective of the atmospheric CO2, which is 415 ppm, it is highest in 8 lakh years. I tell again, it is highest in 8 lakh years. And the target which I was talking about in 2015 Paris Convention, which is 23 to 27 gigaton of carbon dioxide emission equivalent, pledge shortfall by 2030. So we are into really a different kind of situation. Really, we need to work. We need to think of it about our sustainability. Now, to understand the green steel triads, where we can attack and where we can work to bring down that carbon dioxide to become zero level. So I have decided this, I have divided this into the green steel triad, which I have coined this word. This is mainly three-pronged action, which we can think of it. One is carbon minimization through fossil fuel inputs, through hydrogen-based, which we are talking about, renewable energy targeting net zero by 2050. Then it is energy efficiency, which is capturing the waste heat, deploying induction heating, and optimizing the process flow to reduce total energy intensity. And the final one, the resource optimization, is maximizing scrap utilization, closing material loops, and ensuring every byproduct is valorized. So these are the three-pronged attack, which is making a triad, which I will be talking about. So let me talk about the pillar one, which is renewable energy integration. Now, in the renewable energy, if you see that if I talk about solar and wind power generations, it has to be on-site. So if it is on-site, so what will happen? You know, we can directly shift from the fossil fuel power to solar and wind energy. Also, the energy independence, which is, you know, sometimes, you know, the supply chain, there will be grid failure and all those problems will be coming. If you are making it in on-site, then there will not be any problem on that. And the main is these solar and wind power is scalable. If you give the land, you know, you can just increase it and it can grow anything, anywhere else. If you see the Tata Steel, this is a used case, which is the Tata Steel has put solar plant 3 megawatt on-site solar capacity, and which is saving around 5,000 tons of CO2 offset annually. Now, if I talk about hydropower and biomass co-firing, so hydropower is something which is, you know, really it can run heavy industrial generators. It is also very, very stable because the water flows from the top to down, and there is no stoppage of that. So you can, you know, just like that, believe that system, because sometimes the electrical power can go out. So in India, what we are doing is that we have already installed 45 gigawatt, more than 45, it is almost touching 50. In India itself, we have already installed in that. And the second part is biomass, which is co-firing. You know, sometimes I was talking with Professor Julfi about using municipal waste, you know, biochar, biomass, everything, so that, you know, immediately you can take actions of reducing the coal, which is, you know, which is really creating problem for all of us to live. Now, this is another strategy which I am going to put, is that low-hanging fruit strategy. You know, there will be some trees, you know, sometimes you may not be reach at the top of the tree. To reach the top of the tree, you know, it will be difficult for you. So what you will do is that nearby the fruits, you will try to grab this, isn't it? So whatever is in your own hand, you just try to grab those and utilize this. So this is what is the strategy, is waste heat recovery. Whoever is using any kind of plant, you should think about capture the waste heat, and then it converts into electrical energy, or any other process system, process steam also you can convert it, and then it can be reused, and then you should monitor that. So whatever you are capturing, you are reusing, also monitoring. So this is what is called low-hanging fruit strategy. Now, if you see the renewable matrix, it looks, you see that the solar and wind is winning a margin of 15%, with 35%, its largest direct emission reducer. And then hydropower, it is 20%, and then biomass 15%, and waste heat recovery is 12%. Now, the second triad, which I was talking about, is that hydrogen. Everybody has talked about hydrogen. There is really a very good work going on all over the world. You know, this is the catalyst, and you see that this is why it is being replaced, as because the Fe2O3 is converted to Fe in place of carbon. So the decarbonization looks easier for, when you are using hydrogen. But point is that, which somebody was talking about, it can be stored, it can be transported, it can be deployed, but there is a problem of transportation, there is a problem of storage, there will be, usage of problem. So all of us should think about, when you talk about hydrogen, when you think of using hydrogen into your process, you need to think about these things. Otherwise, the whole thing goes, beyond your hand. And the next is that, if you see the hydrogen, it contains 3x the energy per kg for conventional fossil fuel by mass, and it is scalable. So it is the catalyst for the change. Really, that is why the subject of this seminar is really apt, and it is timely. I should thank, organizers for this. Now, if I try to understand what is exactly the hydrogen, there will be some color hydrogens, black, brown, gray, blue. The black is from coal gasifications, and the gray is from natural gas, and blue is natural gas and carbon capturing and storage. So these three, it is better to avoid. Also, there is some, blue light or green light, I should say. There are production of orange hydrogen, which is nuclear powered electrolysis of water, and then yellow, which is solar powered, and wind and hydro electrolysis. So this is the target. So you need to produce, it's not only hydrogen, it has to be green hydrogen. Point it. Now, these are the processes which everybody has talked about. I'm not just going into details of it. It's green hydrogen production and hydrogen shaft furnaces, direct reduction iron, direct reduced iron, and electric arc furnace. If you are taking care of these four processes, you are going to, reduce the 95% of, it can replace the carbon, the fossil fuel, and water vapor will be, it can be a byproduct of it. Now coming to the electric arc furnace, if you see the graph, electric arc furnace is a very good technology, very good, it is a core technology. It is flexible. It also is scrap compatible. You can use more amount of scrap into it, and also the lower capex. The capital expenditure is very, very low. And if you see the conditions which is current, it is around 19%, and it has to be reached by 33% by 2050. And the blast furnace part should come down. Okay. Now coming to the induction furnace, this is another way of bringing down the baseline energy consumption while delivering repeatable and precise temperature, because induction furnace is it is very, very energy efficient than the 45% of the combustion furnaces. The precision control, it can control up to 2 degrees centigrade, so you don't require to heat it more, so that you can conserve some kind of energy. And then, you can, there is no NOx and SOx, which is another problem, which is going to come into the, atmosphere. And you can save some time, as because the induction heating furnaces are very, very, faster. So this is another way of doing things. So this is another idea which it came to my mind, is that, sometimes there are some precision items or precision equipments which are sometimes casted and melted and then casted. It requires a lot of effort and lot of loss of metals, lot of energy, everything. So if the new thing has come, I think somebody is from mechanical engineer, I was talking with him. So the mechanical engineers have come up with a new idea, which is additive manufacturing. It is not subtractive manufacturing. It is a near zero material, waste material. You can plan, design, and print. Like, your photo, you want to print in a printer, you just put the photo and then print. Similarly, equipment and any kind of spare parts, if you want to print, you just put it into the design and then print it through the metal. So you get directly that metal, so there is no wastage of it. And then you see the precision, when you draw in a proper way, so you get a precision control manufacturing. Also higher strength to weight ratio, which is steel is also a very good higher strength to weight ratio. Also the rapid prototyping. Sometimes what happens, you make and then you found that there is a holes and there is some mistakes. So the whole material goes waste. So it's better to have in the design form and understand that and then prepare it. So that your spare parts and whatever you are making, maybe some gold, some precision parts of any machine, you just print it so that you don't require any kind of energy, that kind of energy which is required to melt and then cast it. So now the circular economy, this is the third part which I was talking about, the triad, third part. It is something, this is a closed loop schema, which is raw material extraction, and then you produce, and then you use the phase and products. Again you collect back, and then you scrap, the process is the scrap and then recycle and then put it. So this is, you have to do is that the maximization of reuse and minimization of extraction. So this is what is circular economy is talking about. Now India, in case of India, we can tell you that we are using around 25% of scrap, as of 2024, and our target is 2030, which is 35, and in 2040, which is 43, and the mandate is we need to reach at least 50% of the scrap in our steel industry. And if you see the point is that 1 ton of scrap recycles 1.4 ton of iron ore as well as 0.74 ton of coal. So this is one thing. Another thing is that because India, after the independence, in 1947, we got independence, and 2025 it is around 80 years, we have reached 150 million ton. Last year we have produced 153 million ton, and the target is 2030 is 300 million ton, and then again from 2030 to 2047 we will be reaching 500 million ton. So see the rate of production of steel. Last 75 years we have reached 150 million ton, and next 4 years we are going to double it. See the rate of going for the production of steel. So once you are going in increasing the speed, the Mercedes-Benz goes 120 to 140, you need to be more careful, isn't it? So that's why India is into that zone to produce, to become, already we are in the second largest steel producer after China. It's like, somebody scores 90% or 95% in a first boy has scored 95 and the second boy has scored over 15. Does it look good? It doesn't look good, isn't it? So it's like China is producing 1,000 million ton and we are producing 150 million ton. It's first boy 90 and second boy is 150, 15. So we need to be at least reaching 50. So that's the target. By 2047, we are going to reach 500 million ton, And then the circular economy, when you use this, it is going to give you longevity. You can see when you use more amount of scrap, what happens, sometimes if you reuse, in India we are reusing the scraps after 15 years of car. In a car there are 17 to 18 types of steel are being used. Now the design should be, when you put it scrap, you see, when you are separating it, these scraps, it becomes very, very difficult for a steel maker or a scrap manufacturers who are making. They find it really difficult to separate it out. So if I can design a car which is having a single metal of low alloys, which, and the mark which I was talking about, the standardized marking and the digital material passports, if we can mate in that, like, chip into that metal, so that the separation becomes very easy. So when you make a car and recycle the car, if you use this kind of technology, it is going to help, bring out more amount of scraps into the system, so that circular economy goes better, Now I was talking about the valorization of whatever the steel produce. It is already BF slag is being used In cement industry, everywhere, the blast furnace slag can replace 40 to 70% of the clinkers, which is cutting cement CO2 footprint dramatically. Also, the road constructions and the fertilizer productions, there are umpteen number of usage of the slags which are being produced, or which are being produced into the steel industry. So now, if I go to the global scenario, this is SSAB, LKAB, and Vattenfall joint venture 2026. Morning, Professor Julfi was talking about that. It is 2026 commercial scale target. And if it goes right, if you see the timeline, 2016, 2020, 21, and 26, 95% of the carbon reduction with a conventional blast furnace, and the technology is H2 plus DRI. Now, there are other steel makers, which is bigger steel makers like Nippon Steel and ArcelorMittal. They have come out with a smart carbon strategy, and Nippon Steel has come up with eco-process programs. These are the programs they have. Each steel industry is targeting about reduction of the CO2 by at least 30 to 40% of their usage. Now, this is another kind of innovation pilots which are being used by European some steel companies. These H2 Future, Voestalpine, they are our largest electrolysis. They are going to make within the steel works. They are going to make electrolysis plant, and they produce hydrogen directly on site for DRI trials using grid renewable power. In Belgium, Steel and All, ArcelorMittal, they are also using some kind of technology, carbon pioneering, carbon capturing utilizations. In Hisarda in Netherlands, they are also using some kind of technology, which is innovative pilots. Now, this is a Indian answer to some kind of usage of recycled circular economy. Kalyani Firasta is India's proof point, and it has saved around 76,484 tons of CO2, which is 70% of the recycled scrap. And you see the 99.4% of the waste recycling rate, and 10% also it has reduced the water consumptions. Now, after understanding these, what is the strategic outlook and the barriers? So, what is the road ahead? The dividends and the friction points, as well as the path forward. Now, if I see the strategic dividends, if we do good, what will happen? Sometimes, students, they say, sir, after if I pass with the 90% marks, what should I get? What is the gift? What is the, award I'm going to get? So this is what is the award a country can get in India, as India. You see that 7.3% of the boost in Indian annual GDP from reaching net zero by 2050. Also, there will be more than 20 million jobs will be created when you transit from green steel to 2050. Now, this is also going to help us is that there is energy security. There will be, CBAM is being used now by Europe. So there will be a premium of the steel cost, 15 to 25% of the premium price, which India is going to encash. And also there will be a technology leadership. When you shift from new kind of technology, you have the patents, so you play with the customers. Now, what is the reality check? If you see the reality check, we need to produce this much of green hydrogen. And now 1371 gigawatt of hydrogen and this much of to be produced. It's not only the production. There are, which I was talking about, that the bottleneck is green steel is no longer just metallurgy. It is land availability, the grid efficiency, and the mass scale clean energy generation. Sometimes back, India reached 48 degrees centigrade in India. There was a temperature, and that day, everybody started using the air condition in their home. So the grid almost reached generally grids, they work around 40% of the capacity. So that day it reached around 60%. So that was a check. Sometimes what will happen after sometimes, this may reach up to 70 to 80%. So grid may fail. So once grid fails, the whole country will be dark. So that will be the issue. So if we don't understand this, then it will be a problem for us. This is what is reality check. I am talking about the next generation people, the students, those who are hearing me. So please think of that also. Now, where exactly we are standing. If you see, the blue part is required gigawatt, and we are on track of maybe less than the half. So we need to back up. We need to work more. We need to think up. You need to come up out of the dream and then think of doing something. It's not playing in your bed. You have to come to the field. Now, what are the friction point? What are the key barriers which you may sometimes face while incorporating these kind of ideas? So first is capital. So you need to be when you retrofit a legacy blast furnace and building of a new hydrogen DR facilities, hundreds of billions of dollars have to be into investment is required. There will be renewable grid capacity, 1371 gigawatt of additional renewables. There will be green hydrogen supply, and there should be some kind of policy alignment. Also the workforce transition, which is the student. You should know when you think of green hydrogen technology, you should think about the running of those kind of technology into your field, and also the supply chain readiness. You should be, the chain should be proper, otherwise there will be a failure into this. So these are the main friction points. And to conclude, this is the immediate efficiency, what is to be done. I just don't want to go details about it. 2026 to 2030, you need to scale up the hydrogen, and 2030 to 2050, net zero deployment. It's not single. All three has to be done simultaneously. It's not that we reach 2030 and then do something. No, we should start everything doing good, isn't it? So just to conclude, I would like to call upon all the students. I'll tell you a story and then complete it. Is that Lord Rama, when he was making a bridge from India to Sri Lanka to go to Lanka, there were all kind of monkeys. They bring the stones into that sea, and they were putting it. So everybody, big monkeys, they brought big stones and then put it. Finally, the bridge was not, finally it is not 100%. So then finally one small squirrel, he came and he started asking, Lord Rama, what could I do, help you? I am a very small person, what could I do? So Rama told that whatever it fits your mouth, you take that amount of stone and bring and put it there, so that it completes the 100%. So I request all the students, you become squirrel and you contribute from your side, so that the green hydrogen technology, green steel technology, decarbonization journey is 100%. Let's make our world cleaner, greener, and sustainable. Thank you.
Thank you. Let's give a big applause to Dr. Arghya. Thank you so much for your very interesting presentation. And next is Q&A. Maybe from the audience, do you have any question? Okay.
Yes, please.
Fazul, please.
So now the question comes, J2A.
Thank you, Dr. Arghya, for a very interesting talk. This is like a conclusion from our today's symposium, how to achieve the green steel or carbon zero steel in 2050. So my first question is about the scrap. You say that you will increase the scrap proportion in India until 70%, 50%, 50%, right? So the
Yes,
question
we are now at 25%.
Yeah. What about the scrap availability? Because now scrap is shortage. Everybody needs
Yes.
scrap.
Yes.
And everybody claim, I will use electric arc furnace to produce steel without carbon emission by using green electricity, and they claim we produce green steel. Every steel plant want to have it. Now
Yes.
the scrap is shortage. So the question is how to get the scrap.
Yes, that's what I have told about that the design of the cars. Mainly the 40% of the carbon dioxide emission comes from the auto industry. So we need to target that. It's not low-hanging fruit strategy. 40% of the most bulk user of this carbon emission is coming from the cars and the vehicles. So these spare parts which are being used and the car design has to be such that the steel which are being used, even you know, the steel which are being used, that has to be a single quality, so that you get more amount of, now the separation of these scraps are really, really difficult. All of us are struggling. Even you know, a small thing I just want to tell you is that in car there are 18 types of steel are being used for different kind of applications, right? Now, if I bring it down to 3 or 4 kind of steel, which gives the required, you know, purpose serving for the automotive industry. So what happens, my scrap, you know, separation is becoming very, very easy, one thing. Second thing is that the life of commercial vehicle, we have already has got some policy for that 15 years of running a commercial vehicle, you need to scrap it out. So these has to be very stringent. There is a policy, but it is not yet stringent, that is not in the road. So these are the small steps. Each people has to think of that. So these are the things we are planning. Even sometimes back we were using, you know, the iron ore of less iron, like 30 or 35% of iron, which can be, you know, replaced as a scrap. So there are studies on that. Those things also can be thought of. So these are the only small things I can tell you as of now.
Yeah, but if we see now the current situation, more than 50% of steel is used for construction, for housing, for building, for road, for bridges. So I think for automotive industry is less than 20%, right? Less than 30%. So it means that if you need a lot of scrap to feed the steel plant, so we need also to
yes, agree. Completely agree. That's what we are also struggling. You know, all of us are thinking about the scrap shifting. See, 51% now. 10 years back, 10 years down the back, you know, blast furnace was producing almost 80% of the steel, and 20% was from the electrical furnace. 10-15 years back. Slowly it has gone such a way that now 55% of the production is from electrical furnace, and 45 blast furnace percentage has come down. But again, I tell you one thing: people are going for bigger blast furnaces when you are going for a, you know, sometimes going for the production of steel. People are going for bigger blast furnaces also. So there is a strategy, you know, conflict. Which, that's what I talked about the policy. The policy has to be very, very clear, otherwise we will be failing the way we have been failing. So it is very unfortunate for all of us. So we need to work on that, absolutely. Thank you. Thank you so much. Thank you so much. Thank you one and all.
Thank you so much. Interesting discussion. Okay, maybe from the audience, do you have other questions? No? Okay, so give applause to Dr. Argia. And so my job as moderator is finished. I will move back to the MC. Thank you so much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
wabarakatuh. Okay, thank you to Mr. Fareza for facilitating this session. Please give another applause for Mr. Fareza. Distinguished guests and participants, now we have come to the end of the day one of Indonesia, India, Australia Symposium on Frontiers in Hydrogen Metallurgy. On behalf of the organizing committee, we would like to express our sincere gratitude to all distinguished speakers, moderators, participants, and supporting institutions and partners who have contributed to the success of today's event. Please give applause. We also extend our appreciation to all committee and supporting teams for their dedication and hard work throughout the preparation and implementation of this event. We hope today's discussion, collaboration, and exchange of ideas will contribute to the advancement of sustainable metallurgy and hydrogen-based technologies in the future. For all VIP participants, Tomorrow agenda will continue with a series of laboratory visit and academic activities at the GEM laboratory and related research facilities at Institut Teknologi Bandung. For all participants, thank you for your participation. See you on the next journey and have a pleasant evening. Wassalamualaikum warahmatullahi wabarakatuh.